the product tree and the acquisition masks, and so we can hopefully get some of your feedback in the round table at the end of this session. So firstly, the goals for land ice. C1 is about glacier mass balance, providing a consistent and highly resolved global glacier mass balance, filling major spatial gaps in the current observation of mountain glaciers and outlet glaciers of the ice sheets. The second one is new insights into the physical processes associated with the coupling between glacier mass change and ice dynamics. So the goal here is to improve the understanding and prediction of rapid and abrupt glacier changes and the balance between vertical ice flow and mass accumulation and ablation. Then there are two goals for solid Earth. The first one is mapping all components, and by all components we mean all three dimensions of global tectonic strain and the deformation caused by volcanism and the earthquake cycle. The idea is to constrain the geometry and nature of the driving processes behind tectonics and improve the forecast of the associated geohazards. And the final one is understanding cycles of topographic growth, mass transport and collapse at actively erupting volcanoes, and again, improving the forecast of the associated geohazards. Hopefully most of you saw Paco's talk earlier in the week where he talked about the Harmony mission concept, but this is just a quick reminder. So in the present day, which is the top row on this slide, with one Sentinel-1, we have one line of sight. If we have ascending and descending tracks, we end up with two lines of sight. When we have Harmony as well, Harmony is going to consist of two companion satellites. When we're in XTI mode, those two satellites are both going to be following Harmony. So that will give us 2 lines of sight on each track, 4 lines of sight in total, plus a digital elevation model. And in Harmony stereo mode, there's going to be one Harmony ahead of Sentinel, one Harmony behind Sentinel. That'll give us 3 lines of sight per track, but of course no DEM, and 6 lines of sight in total. So this is the product tree that Paco has already shown you, and for the purposes of today's, this particular talk, the key thing to note is there's 2 branches here. So this branch on the left is focusing on topographic change, and this is going to be available in XTI phase only. This branch on the right here, this is focusing on the 3-dimensional velocities. This is going to be available in both XTI phase and in stereo phase, but obviously with slightly different accuracies. Starting off by looking at topographic change, the goal here is to target ice volume change, glacier dynamics, volcano eruptions, landslides and permafrost. So this is an example of the kind of current calculations that people do about glacier mass balance, and this is a key input into all sorts of things, but particularly the IPCC. So the headlines here that we're all very well aware of is glaciers are losing a lot of mass, 273 gigatons per year. That's increasing between the first and the second half of this study by 30%, by about a third. And overall, glaciers have lost about 5% of their ice globally. But the key thing here is this is extremely variable regionally, between 2% and 39%. And there are still large gaps and inconsistencies and uncertainties both on the regional and local scale here. So if you look behind the hood of these kind of compilations, which are extremely impressive, you see something like this. This was taken from the supplementary material of this paper. On the left here, these are all the different research groups and analysis methods they've developed. In the middle is all the different sensors they're using, and on the right are all the different regions. So trying to piece these together require putting together a lot of very diverse observations from different sensors, different research groups, and they work with different sensitivities and biases in different areas. And that's because some of these methods have high temporal sensitivity and low spatial density, others have high spatial density and low temporal sensitivity, and of course the ground-based measurements are brilliant, but they are extremely local in nature. So Harmony is going to sit nicely in this gap here and allow us to produce high spatial and temporal resolution measurements at a global scale. So to do that, we need a mask. So the priority here, as is actually in the scientific objectives, are the outlet glaciers of the ice sheet. So we're focusing on the coastal regions of Antarctica and Greenland, and also mountain glaciers. So to produce the mountain glacier mask, we've taken this inventory, the Randolph Glacier Inventory from 2000. The high priority areas are places where there is significant coverage of large, by which we mean more than a square kilometre, glaciers. So this is the main area we're focusing on. We have a medium priority zone where there are very few scattered glaciers of about this size, and they are maybe not globally important, but they're certainly locally or regionally important. And the ones that we've put in yellow, these are very small glaciers, and remember this inventory is from 2000, and we know that small glaciers are shrinking disproportionately quickly, so it's highly probable, rather sad, that by the time Harmony even launches, that maybe these glaciers won't be glaciers anymore. Anyway. Okay, so moving on to volcanic hazard. It's well known that volcano monitoring reduces fatalities and supports economic development. This is a very famous example from Merapi in 2010. This SAR image showed the growth of a lava dome at the summit of the volcano. Based on this observation, the local volcano observatory increased the evacuation zone shortly before the dome collapsed, caused a pyroclastic flow down the flanks of the volcano, and this observation is credited with saving 10 to 20,000 lives. But the problem is that measurements of topographic change remain very rare. This is one of the few examples we have, and particularly on the timescales that you need for making these kind of real-time observations, but also for studying some of the very rapid processes that trigger eruptions. So the processes that trigger collapses, for example, are very poorly understood. It's not just explosive eruptions where this is important. One of the most fundamental parameters of any volcanic eruption is the volume. That's how we estimate the size of an eruption. And there are lots and lots of methods that we can use for mapping the area of volcanic deposits, but not very many methods for measuring the thickness of volcanic deposits. So this is an example here from Ertale in Ethiopia. The original estimate of this assumed that the thickness was about 0.5 meter to 2.5 meters. That's based on ground-based observations. We went back recently, looked at the Tandem X DCM map. We found that there's actually areas where the lava is ponding up to 27 meters. So our volume change here is an order of magnitude larger than we'd previously thought. And the slide on the panel on the right here, this shows just how important the changing topography is in these areas of actively erupting volcanoes. This is from Kilauea in Hawaii, and it shows the predicted flow paths, the forecasted flow paths, using topography from 2 different dates. So you can see that between 2005, when the blue lines were calculated, and 2013, when the red lines were calculated, there's been a significant change in topography, and it's changed the forecast of where the flow paths are going to go. So understanding the dynamic topography is really important here as well. So these are the scenarios that we've been using for the end-to-end simulator that you're going to hear more about later. So we're looking at lava domes. The example here is from Mount St. Helens, where there's some really nice aerial data. Pyroclastic flow, this is Fuego in Guatemala, where there's some nice Tandem X data. An explosive eruption, this is the Soufriere St. Vincent eruption, where a huge explosion completely changed the shape of the crater and blew away an old lava dome. And there's also Tandem X data here, I should say. And these are all static measurements. But actually, the real benefit of Harmony is going to be that we can make dynamic measurements, seeing how the topography is changing over time. And it's much harder to get a good time series here. After some searching around, we realized that actually Julia Kubanek had the perfect example that she processed during her PhD. And this is from Tolbachik in Kamchatka. And actually, even though this is quite a unique and amazing time series, by today's standards, Harmony is going to do even better. So we then have to decide how to put together a mask for the acquisitions here. So the first question is which eruptions actually cause topographic change. And here I had a master student, Rebecca Edwards. She went back and looked at this Tandem X DCM. It covers the whole period of the eruption, so there's no very poor time resolution on this, but it covers 159 eruptions from 103 volcanoes, and she looked at all of these. She found that we could identify topographic changes associated with lava flows, lava domes, pyroclastic density currents, flank collapses, ash deposits, and explosions, changing the topography. And there were only 45 eruptions where nothing was visible. Most of these were because of the bad data quality in the Tandem X DM. Left 9, and mostly these were very, very small eruptions that either had a little bit of ashfall or they were phreatic eruptions. These are water, sort of steam-driven eruptions where there aren't really very big deposits. So the answer from this is all volcanoes, all eruptions, seem to cause topographic change. Therefore, we want to cover all volcanoes that have eruptions. So then we have to try and predict which volcanoes are going to erupt, and this is kind of like the million-dollar question in our research field. So this is a hard thing to do. But we thought, well, the best way to approach this is to look at the historical eruptions. So the volcanoes that erupt most often are the ones that are erupting all the time. So we did a retrospective analysis. We imagined we were in 2020, and we had the eruption catalogue. We looked back at the past historical eruptions, and we tried to predict how well we would do on the data between 2020 and 2035. So if we stand in 2019 and we look at the past 8 years, we find 145 volcanoes that have erupted. We call these the high priority volcanoes. We find that in the next 5 years, 93 of them actually did go on to erupt again. These are the true positives. 52 didn't. Those are places we've collected data that really don't show anything very interesting. And we missed 20 eruptions. And what's interesting here is actually that number is pretty stubborn. If you extend the timeline of these calculations out to 20 years, you're still stuck with about 20 volcanoes. These are volcanoes that erupt out of the blue that haven't erupted for hundreds and hundreds of years. So it's going to be really difficult to capture those in a high priority sense. So if we put all this together, we're left with this image. So the high priority ones are the ones that have erupted since 2017 and have high quality data in the tandem XDCM. The medium ones are ones that have been erupted since 1800, and we're hoping that we'll be able to actually capture all of the volcanoes as well, even though the majority of these probably won't erupt in the time span of the mission. All right, so moving on to the three-dimensional velocities, TDV. There are going to be two key level 3 products in this phase, so the velocity vectors, which is TDV, but also three-dimensional time series, TDTS. And here we're aiming at tectonic strain and 3D ice surface motion, and also the 3D surface motion on landslides, volcanoes, and permafrost. And this is going to be collected throughout the entire mission, both in XTI and in stereo phase. So a quick reminder about earthquakes. This is a nice figure from John Elliott, which shows very clearly that earthquakes occur in regions of strain, and deadly earthquakes occur in regions where there's high strain and high population. And the Turkey-Syria earthquake was a good reminder of that. So the way people have done this traditionally is using ground-based GNSS networks. You can interpolate these to produce strain rates, and then you can use these to create a seismic hazard map. Obviously, the distribution of ground-based sensors is really heterogeneous, and you can actually do a lot, and quite sparse as well. You can do a lot better using, if you add in Sentinel-1. This is, again, something that John Elliott showed earlier this week. So this is the COMET COMET strain map for the Alpine Himalayan belt. The top panel here is the strain map based on just the GNSS data, and the bottom one is what happens when you add in the Sentinel-1 INSAR. And you can clearly see that the resolution is improved and the strain is much more clearly focused on these faults. And we get strain rates down to about 10 nanostrain or better. But this works really well because Sentinel is very good at sensing east-west motion, but it's much less good at the north-south motion. So this is a simulation of what happens if you have a north-south shear zone, and you try and resolve that using Sentinel-1 and GNSS. Not a great result. If you add in harmony, suddenly you get a really nice, clear, crisp image here. So adding in this north-south component from harmony should hugely improve the resolution of strain rates on these north-south shear zones. So to create a tectonic mask, the first question is what strain rate is important? Well, we can look at strain rates in which these fatalities are occurring. 96% of fatalities occur at strain rates of 10 nanostrain per year or greater, so that's our target, 10 nanostrain per year or greater. To make a global mask, we then think that actually the GNSS is going to smooth that out, so we reduce that down to 5 nanostrain per year, and then we add a 5-kilometer buffer either side of those regions. That gives us our region in total. The medium priority, slightly higher priority, is the Alpine Himalayan belt. This is responsible for most of those deadly earthquakes. And then the highest priority are the Alpine Himalayan belt regions that are dominated by north-south shear, and they're shown on that map in purple. And then also, obviously, we're going to be collecting the three-dimensional velocities for the ice sheets. And here the highest priorities are the Amundsen Embayment and the Antarctic Peninsula. These are the largest contributors to sea level rise. Queen Maud Land, which has the most rapidly changing surface mass balance. And in Greenland, we're going to be looking at regions with velocities of greater than 6 or 7 centimeters a year, and they're shown in the red colors on this plot here. So to bring all of this back together, there's two kind of branches to the product tree: the topographic change, which is going to be collected in the XTI phase, and is going to focus on ice volume changes, glacier dynamics, volcanic eruptions, landslides, and permafrost. And the other branch is the three-dimensional velocities, which is going to be acquired in both XTI and stereo phase. It's going to cover tectonic strain, 3D ice surface motion, and the 3D surface motion on landslides, volcanoes, and permafrost. All right. Thank you.
And this gives us time for some questions.
Thanks, Julia. It's a really exciting mission. I wondered, in terms of the volcanic activity, how much flexibility there's going to be, because obviously many of those 20 volcanoes will go through some kind of period of unrest before they erupt, or there'll be INSAR signals showing that there's something going on. So how much flexibility might there be in the mission?
Well, that's a good question to ask some of the people from ESA who are here. And we hope there will be a lot of flexibility, but we need a starting point. And we also hope that we will be able to acquire data routinely over all of those low priority areas. For the topographic change, probably, so for some volcanoes where there's large topographic change, we're going to need a time series before the event occurs. So the high priority ones are the ones where we're probably going to focus on getting the time series good enough, early enough, and then the other ones will probably come along a little bit later. So the idea is that we should get everything, but the good quality time series may be in place in the high priority volcanoes earlier in the mission than the low priority ones.
Thank you for this nice overview. Maybe my question is a little bit more directed also to Paco. I'm thinking about the modes now that are being supported by Harmony. So the volcanic islands and so on are also captured mostly by StripMap with Sentinel. So does Harmony support the TOPS modes and the StripMap modes, or only the TOPS?
You can answer that.
It supports all the modes.
So all the modes.
Yeah.
So you will actually benefit then from the StripMap acquisition that are being done on the volcanic islands and things like that?
StripMap is the best, right?
Yeah, okay.
Yes. Yeah. Okay, so the next talk will go into the technical details, so we go from science to technical details. And this should be a talk given by Pau Prats, but Pau was sick. So Mark, which is, I don't know where Mark is. Mark is walking, is going to stand in for Pau, and it's going to go a bit more into the products and also introduce the work that we are doing, or that they are doing right now, to simulate and develop the algorithms to get all these nice products that Juliet wants.
Thank you, Paco, for the introduction. And good morning, everybody. Yes, indeed. Actually, my plan was that Pau was going to substitute me in the later talk, but he got sick, and then everything turned into a chicken game, and I had to do it for him, actually. Good. So I will report on the status of the land science project to support the consolidation of the algorithms. And the validation of the quality of the products up to the CDR. Okay. So this was already, yeah. Okay. This is what I just said. This is basically ahead of the system CDR. So there are a number of studies running, and in this particular one, there should happen the consolidation of the land. applications, the land products, the quality of the land products, and the consolidation of the algorithms, and for which we have to tackle a number of challenges, which are listed there, and I will go through them in the presentation. So this is the same diagram that Julie was showing, and in which we have basically the three main processing flows from which we will obtain the different stellar products that we have in land. And basically, if we go through them, then basically we see the different products, intermediate products, which are relevant for the specific applications. On the left-hand side, we see the flow leading to the topographic change and to the DM, for which this is done in close formation and exploiting single-pass interferometry, cross-track single-pass interferometry. In the middle flow, we see the derivation of the three-dimensional deformation velocities or vectors, which is based on repeat pass interferometry, and this is done both in the close formation phase and in the stereo phase of the mission. And in the last one, we see the flow for the fast deformation. Now let's take a look a little bit more into the detail about tools and challenges that are being looked into in this project. The first thing that I will show you is the tool that is used for validating the performance of the products derived from the stacks. So this total this three-dimensional deformation, for which there is a specific simulator which has been developed directly simulating the level one images. The flow of the simulator looks like that. In which there is basically the simulation of a level 1 image, and which is shaped with realistic signatures, and then we try to feed realistic errors and realistic observation according to the radar observation geometry and the characteristics of the harmony acquisition mode. And then from there we get like realistic level 1 images. Remember, we have here something like a simulation of 100 or several hundreds, 100 and something images, and then the computational complexity plays a fundamental role, and this is the reason why the structure of the simulator looks like this. And then basically we see here an example of the inputs that we have, the reflectivity, the deformation map, the atmosphere, the ionosphere, the impact of the clock, and then before the animation, then we have basically the results from the process data. No? We have basically the true processing running, and then evaluating the results, and then evaluating the quality from the simulated data. And this allows us, of course, to say then the performance is achieved according, or the performance is in line with the specification that we have. Some of the things which have been done are evolutions with respect to the status of the simulator in previous phases. Here, the important one is to note that there is this integration of the level 2 processor. So the level 2 processor is more sophisticated than it used to be, which plays a fundamental role in the credibility of the results. And the 3D immersion tool has also been incorporated. So this integration of this processor is ongoing, as I was saying. Good. Another example is another item which has been, or another number of items which have been consolidated over the past couple of months in the frame of the study, is the consolidation of the algorithms, of the processing algorithms, and the ATVDs have been delivered to ESA, or first versions of the draft versions of the ATVDs have been delivered to ESA. Here we have a couple of bullets with some characteristics of the algorithms, which we have like distributed targets and MPS processing chain. Some details about the phase unwrapping, some details about the use of annotation corrections for the data. And the second element that I was mentioning before is this integration of true PS processors, so basically it's Python versions of stamps which are running currently, and this is PyStamps and StampPy. This allows, of course, to have Python prototypes. This allows to test things and to integrate, to update, or to further develop the algorithms and the calibration approaches, which is, of course, a fantastic thing for the consolidation of tools which will be used during the mission. Something additional on top of this is for Landais, on top of usual linear processing. So what we have also for fast-moving regions is the consolidation or the use of speckle tracking for trying to estimate the deformation observables. From which basically the whole processing approach has been developed, and according to the agreement, there will be basically based on the estimation of range offsets. Something else which is more related to the simulation of single pass interferometric data. For which we were extending a tool that we developed some years ago in the frame of the SAOCOM-CS studies for ESA, which is a simulator for bistatic and multistatic systems. This has been extended for the case of Harmony. And here we have a couple of examples of things that we were doing with it, like analysis this looks like boring, but this was done in the frame of analysis looking into the optimal steering possibilities for Harmony, and in particular for the optimization of the analog track delays. And here we have like a couple of point target responses simulated with TOPS, and also with the extreme squint angles that Harmony sees. A couple of synthetic data with different, don't remember, I think different degrees of ambiguities and signal-to-noise ratios, and a couple of examples with clock errors and with synchronized database data. Again, a list of the things which have been done over the past couple of months. Some of them were already available. In particular, there are a number of things that will be shown in the upcoming slides, so I will not spend too much time discussing them. This status of the processing algorithm, this is both for description and for this is both for description and also to illustrate a little bit the challenges that we're facing here. Basically, we have a situation in which, because of the high squints, we have two effects here. So we have basically a Doppler centroid which is changing with range, which is changing a lot with range. So we have basically a shape like this. If we take a look at a linear shape, if we take a look at the Doppler centroid with the range, but we also have the situation in which this Doppler centroid also changes with the range frequency, as expected, which leads us into shapes like this of the spectrum. And then this poses a problem for efficient processing, especially if you want to do it in the frequency domain and you want to to save computation and to do it properly, not make any approximations because of the large screens, we believe, and because of the tight requirements, we believe that we cannot afford any many processing errors or many errors coming from the processing. Now, the current baseline that we were doing was in integrating into the simulator was just using GPU based of the direct back projection. But here the tricky part is how to define the grid. So as you can imagine, based on the spectrum that I just showed. But here we have two options. Basically, this one, which is integrated in bistatic end-to-end, and there is another option which is running, which is the integration of the Fourier-based GAFA processor. The good part of this approach with the GPU is that it allows us to have like a golden model, no? With which we can compare, because in this one we have like all kind of corrections that we want to have, no? So we have perfect accommodation of the screens, of the orbits, of the topography, and then we can aim at profiling what is the impact of the approximations that necessarily are done in any kind of Fourier-based approach. Here we have like an example before focusing or even the raw data and then after focusing. For the DM chain, for the interferometric chain, basically we have like standard things, geometrical registration, then spectral filtering. I will show a slide on this. And basically a breadboard processor which is being developed tailored for the Harmony mission. Again, bistatic and then with these large screens, which is being done by Olivier Dont, based on the EO tools. An example, but I think this is quite standard. Yeah, it looks standard. Getting there is a little bit trickier, but yeah, I mean, we have basically the interferometric pair, the computation of the coherence of the interferograms, then unwrapping and calibration, and then the phase-to-height conversion, and which you see basically that this was coming from the simulated DEM itself. So this is an artifact which is coming from the DEM. An example here of the azimuth filter, and here it's an interesting thing because basically here what we have is a simulated a case in which you have 500 meters along track baseline. So it's not the Ukrainian flag. And one is the blue is one of the images, and in yellow is the other. It's 500 meters along track baseline, as I say, and basically this is the result before and after spectral filtering. Now, as you would expect, there is this enhancement of the coherence, but this is not the interesting thing. The interesting thing is to see that to do properly the spectral filter here, we have to follow the shape of the spectrum. If you have your data in this, let's say in this sampling, no, in this sampling grid, no. Yeah. It's interesting to see because many elements of the processing, not only the spectral filtering, but also the multi-look, also the database synchronization and so on, will have to access the looks. And basically this problem will be replicated throughout the processor if it's not solved in a generic manner. And we believe that the way to go to try to have like a proper handling of the data is basically to have like a spectrum like this. Well, immediately you see that from the terms of data, this would be more efficient than this one, no? Because basically, if you want to avoid having trouble whenever you have to upsample, interpolate, doing things like that, accessing looks and so on. So basically, it's very easy to fall into the trap of adding additional samples, unnecessary samples here, which is something that you can get rid of if you use a geometry or a sampling like this one. But as I say, as I was mentioning before, it also gives the opportunity and the option to accelerate many of the operations done during processing, accessing the different looks. Good. Here an example, just to show also that enhanced spectral diversity has been incorporated. So usual ESD for the estimation of along track orbit errors. And this is an example of simulated data with the simulated interferograms. This would be with the output of the enhanced spectral diversity. It's running as expected. It's estimating also what it should be coming based on this 10 centimeter azimuth error that we have here, which it sounds as large because we know from TandemX that we have millimeter baselines, but these millimeter baselines, it remains to be seen when they will be available. So it's good to have. And then that's the output of after correcting. This was, for instance, a simulation in which basically this orbit error was only available, and then after correcting it, then running ESD again, then it was basically giving us something flat. An interesting thing here was to note that because the geometry is true, let's say, because we're using reference orbits and then adding the formation or the baselines and the formation as it should. An interesting thing to see is basically that because of the squint and because of the saturation of the Doppler evolution, we have like this modification of the effective separation between the two looks that are accessed by the ESD. Yeah? Good. Another example is the incorporation of clock errors into the data, and this is just basically having different realizations for the three bursts. This is a case of three bursts. Sorry, a case of three subswaths, no? This is a case of three subswaths, sorry. And then basically we have here the coherence, which is only slightly affected. The errors are added without a frequency, and this is why the coherence looks pretty good. But we see the fringes, the clock fringes in the residual interferograms, and we see it also in the recovered DMs. Again, with the same artifact that we had before. So this is not coming from the clock; it's just this thing here that we see. Yeah, don't. I already anticipate. No, don't look forward to it because it's going to be a lot replicated. Okay, good. Way forward. In terms of simulators and in terms of algorithms, no, both are necessary. Well, the consolidation of the algorithms for sure, and then also the simulators to show that the performance is achieved with the current processing baseline. Concerning this HIPS Terra, which is the name that the simulator has for the project, and then basically there is an improvement in the system characterization in the forward models and also in the reverse processing kernels, which is still ongoing. For the reverse processing kernels, we're going to use ideally a different one than the one which has been shown here, and the idea is to go for a reverse fast factorized approach. And for the level 1, level 2, and level 3 algorithms, so basically you have everything which, or part of the things that were discussed before, which is basically see the different elements that were mentioned before. This is everything. Okay.
Great. Thank you, Mark. Anyone have any quick questions?
First of all, thank you very much for the presentation. I have a question regarding the Python implementation of SAMs. Why are you keep having two different repositories for it? Or are you planning to focus just on one algorithm at some point?
I didn't get it. Can you repeat the question, please?
So far you're presenting that you have PyStamps and Stampy for the PSI processing. Are you focusing on one of those repositories at some point, or what's the reason for the redundancy?
This is basically two parallel developments conducted by different people, different teams. And yeah, that's the reason.
Yeah, because I had the same question when I was presenting the same thing on Monday. And so PyStamps is just a translation of stamps to Python, which is working and is being developed. The other one is a more research-oriented tool, which is incorporating the things that are necessary for Harmony, but not only. So they are diverging things, but the one for Harmony is the second one. Yeah.
Thank you.
Okay, we should move on to the next talk. Thank you again, Mark. The next talk is Andreas.
Okay, yeah, hi everyone, I'm Andy Benedicta, and I will address a little bit on how we are planning on tackling the signal penetration for generating the Harmony XDI products over ice sheets and glaciers. And yeah, I try to keep it interesting by focusing on aspects that might be, let's say, a delta on this topic compared to what you may find in literature. I also want to acknowledge all the colleagues you see here, which are involved in the Harmony land ice study. Okay, just a quick recap. So the Harmony XDI phase, we have Sentinel as it's operating as a illuminator, and the two Harmonies in a close formation operating as a cross-track interferometer in a receive-only mode. So to some extent, it's comparable to Tandem X, but as bistatic receive-only satellites. So for land ice and in the XDI phase, the products that are being generated are, first of all, digital surface models, which are then used by combining several DSMs over time and differentiating them to generate topographic change products, and from this derive mass balance estimates over glaciers and ice sheets. Okay, the obvious challenge here is, as everyone probably here in the room knows, that radar signals for example, at C-band, the Harmony Sentinel frequency, partially penetrate into the volume, into snow, fern, and ice. So our phase center may lie somewhere within the volume. If during the two DM acquisitions, this phase center changes, this obviously would lead to a misinterpretation of penetration bias change into a mass balance change, which is not what we want to measure. You might argue, okay, let's just acquire the two DMs at the states where we have the same penetration into the ice and everything cancels out. But first of all, we don't want to restrict ourselves to such scenarios, and also it's not that easy to identify scenarios where, let's say, everything stays constant and we're good. So the aim here is to estimate this penetration into the volume and get back to the surface by correcting this this elevation bias that we get from the signal penetration. A quick, let's say, overview on the scenario that we're facing. So our radar signals are partially penetrating into the volume. So our phase center lies somewhere within the volume over ice sheets and glaciers. And we know, like there have been several studies on that in general this penetration bias how it's called, can be estimated by inverting the magnitude of the volume coherence to then retrieve the surface height. So we are basically going from the height of the phase center at the estimated penetration bias and go back to the surface height. There's one important aspect to that, which I want to highlight here, that actually what we're seeing, so the height that we're measuring with INSAR, actually does not accurately replicate this physical phase center height. And the reason for that, it's obvious. So generally, like the INSAR DMs are generated assuming free space propagation, because we don't know where the actual surface is lying before we measure it. But in reality, the propagation through the volume introduces a different propagation velocity and also refraction effects at the surface interface. This means that the height that we're measuring with INSAR does not replicate the physical phase center height, but is a biased version of that. This might appear obvious to some of you, especially the ones who come with a tomography background, but if you look at the literature, this is often, or in most cases, this is just neglected. But we believe that it's important to consider this, what I call here delta H2 part, which is basically the difference between the physical phase center height and the apparent height that we're seeing with INSAR. Okay, we can also quantify this effect, and I believe there are two valid interpretations of this. The first one is rather like a SAR interferometry interpretation, that the vertical wave number in the volume is stretched with respect to free space propagation. And we can then write this out, and we see that this additional, what I call here propagation bias, delta H2, is basically it's a modulated version of the phase center depth, modulated by the permittivity of the ice and the acquisition geometry. The second interpretation, which leads to the same results, but it's, I think, interesting to consider it, it's more the SAR tomography interpretation of this by interpreting it as a delayed and refracted beam, where we then see that we have like this difference between the physical phase center position and the apparent position as we see it in the generated INSAR DM. And then by just solving the geometry here, we can get an expression for the additional height offset, and we also get an expression for the additional, let's say, horizontal offset. If we look at the numbers that we're getting, so I plot here for 3 different phase center depths, so 5, 10, and 20 meters over different incidence angle. In black, you see this propagation bias error, so the height error. And if we look, for example, at the dashed line, the 10-meter penetration depth, we get additional, let's say, errors of up to 4 meters. So it's a substantial contribution that should not be neglected. Okay, how can we incorporate this whole penetration offsets that we're facing? In our opinions, we shouldn't just deal with it by a 1D correction, by just correcting a height offset, but rather, let's say, appreciate or acknowledge that it's like a 3D geolocation error. So it's not only a height, but it also propagates into the horizontal direction. There's actually a quite easy way to do this by just incorporating it in the overall, let's say, DEM generation flow. So we estimate the magnitude of the volume coherence by isolating it from the total coherence. And from there, based on a uniform volume assumption, we estimate the corresponding penetration phase and also a corresponding range offset. And then we just do the interferometric DEM generation, so this interferometric, let's say, geocoding, where we solve for the interferometric phase, the range sphere and the Doppler cone, and offset this by these 2 quantities, the penetration phase and the range offset. And this will naturally directly bring our DEM at the right position at the surface. What's interesting to note here is that both these corrections, so the correction for the phase and the correction for the range offset, are independent of any knowledge of the permittivity of the volume. So we don't need any density knowledge of the volume, which appears to some extent a little bit counterintuitive at first. But the point is, we're just correcting basically a phase. So we estimate the phase and correct for it, and also the range offset just depends on the phase. So we actually don't need any density knowledge for doing that, which of course is a benefit. Okay, here's a simulation of this based on the bistatic end-to-end that Mark was mentioning beforehand. So we simulate here a scene over British Columbia, a glacier scene, where we generate raw data, where we also inject the volume penetration and then process it until the digital surface model products. You see here the reflectivity and the synthetic penetration depth that we are injecting into the data. The parameters you see here are, let's say, in line with the Harmony system. So here are the results of that, where I show the error in the surface elevation retrieval that we are doing. On this side, you see if we are just compensating for the penetration bias, so the depth of the physical phase center, which is, let's say, what you see as a standard correction in literature, where we see that we are left with, over the glacier areas with about 2 meters of error. This is if we are also accommodating this delta H2, this propagation bias effect, where we see that most of the error is gone, but we are still left with some residual areas at the abrupt changes between penetration and non-penetration. And this is when we do the processing pipeline as proposed on the previous slide, where we also account for the range offsets, where we see that we remove all these residual errors. Okay. So far, I didn't mention any, let's say, of the bistatic characteristics that are introduced by the very large squint angles that Harmony is operating at, so 20 to 26 degrees. Of course, this is just a geometric squint angle. The effective squint angle is less than this because we are in a bistatic mode. But still, there are some effects coming from that. So first of all, like there's a slight change in the two-way penetration depth that we're getting if we're considering the same penetration length compared to a monostatic system, but the impact is rather mild. So you see in blue the bistatic two-way penetration depth versus the monostatic two-way penetration depth for a penetration length of 5 meters. So the impact is for Harmony always less than 5%. We also have a modulation of the vertical wave number in the volume, because we also need to consider the, let's say, the refraction of the squint geometry into the volume, which in total leads to a modulation of the overall complex volume coherence. But as I said, like it's a rather minor impact, and I also don't show more details on this now because there was a interesting talk, and there's also a paper from Georg Fischer from OISAR who assesses this in more detail here. But let's say the main points are that we only have a marginal change of the complex volume coherence, so we don't expect a significant impact on performance. And we also believe, or we have this already in place, how to accommodate this bistatic geometry also then in generating the DSMs. Okay. So far, I always assumed, okay, we are this uniform volume assumption that we are always using to estimate the penetration from the volume coherence is valid in all places. We know that this is not the case. So we also looked into some ideas how we can deal with scenarios where this might not be the case. So we looked into, let's say, into an idea how we could, for example, use multiple interferograms that were generated with different observation geometries of the same scene to get additional information about the penetration and potentially correct for it. The basic idea is what you see here. So we have the same drawing as beforehand, but this time we might have like 2 acquisitions with different baselines or different incidence angles of the same scene. This might be, for example, acquired from neighboring orbits, which is especially should be especially available at higher latitudes. You see here, for example, over Greenland, the maximum incidence angle difference between different orbits, where I just consider here the Sentinel-1 incidence angle range and only descending passes. So this is not aligned with the Sentinel-1 acquisition plan, but this is in general what Sentinel-1 could access. No? Just to give you a feeling that we have relevant different observation geometries. Okay. The problem is that the inversion is not super straightforward, because we know if we have a different observation geometry and we have a volume backscatter scenario, that we are not sensitive to the same phase center. So the phase center depth changes for the different observation geometries. If we write this out in a, let's say, in a simple equation system, so we have like the surface height with respect to the reference stem scaled by the vertical wave number, and we have the penetration depth scaled by the vertical wave number in the volume, and this for both interferograms. We see that we have a system with 3 unknowns and 2 equations. So this is not, it's not that you can directly solve for everything by just using 2 geometries. Again, we can underlie like a certain assumption of the volume distribution, the vertical volume distribution. If we again use this standard uniform volume assumption, we see that we can restrict the system to 2 variables. Again, the surface height with respect to the reference dm and the penetration length into the volume. And this is a system that we can solve numerically. And again, here it's important to note that the surface height retrieval is independent of any permittivity knowledge. Yeah? We did tests for this, both on airborne data, but also tandem X experiments to just prove the concept, and this is one example of this. I also want to say that this is work in progress, but I still want to show it here. We have 2 tandem X acquisitions with different observation geometries. So one has a height of ambiguity of 12 meters, the other one about a factor of 2 more. Here you see the acquisition scene, which is in the Greenland percolation zone, and here you see the 2 interferograms where you can appreciate the different, let's say, fringe rates of the different interferometer sensitivities. This is the digital elevation model in the area, and overlaid some LiDAR tracks from Operation Icebridge, which I will later on use as basically as a validation reference. So on the right side, you see the two acquisitions, the phase and the coherence, where you again note, okay, we have in the first acquisition with the smaller height of ambiguity, we have a stronger decorrelation from the volume. And we use these 2 phases, so this is a phase-only inversion to basically retrieve the surface height from these 2 INSAR phases with respect to the Copernicus DM. So just using the two phases, and here you see the comparison to the LiDAR reference. So in orange you see if no penetration compensation at all is used. Yeah? And then in green, you see the nominal correction, where we use the magnitude of the coherence of one of the acquisitions, which brings us quite well back to 0. And then in red, you see the approach that I just outlined, where we use the 2 interferometric phases to estimate the surface height, which also brings us in the direction of 0. We have a slight difference, which is which we need to still interpret. My feeling is that the reason for that is that it's not a perfect uniform volume. So the 2 predictions will go in a slightly different direction, and I also wanted to illustrate this here. So if we have not a perfect uniform volume, but a uniform volume which we basically where we superimpose, like for example, a layer, we see that the different estimations, so in blue and in orange, you see the estimation based on the magnitude of the volume coherence, and in green, you see it using the 2 interferometric phases. So if you're not having a perfect uniform volume, they diverge. And this is actually nice, because it gives us a certain information content where we can say, okay, this might be an approach that helps us identifying deviations from this uniform volume assumption, and might even allow us to invert a more complex volume. Okay, but as I said, this is work in progress, but I think it's an interesting one, and we will continue working on that. This brings me to the summary. So elevation bias correction is a fundamental aspect of the Harmony XTI products. Conventionally processed DMs over dielectric dense volumes, so for example snow ice, show a biased representation of the phase center. And this is, I think, something to keep in mind also for tandem X and so on. We don't need any permittivity knowledge to do this surface height retrieval, which is nice. We also believe that the correction should be accommodate the full 3D geolocation problem, not only a height correction. We don't expect any major impact or degradation from the squinted bistatic harmony geometry. And yeah, we looked also into an idea of using multiple interferograms with geometric diversity, which might be an interesting options for some scenarios. With this, I'm done and happy to take questions.
Any questions for Andrea?
Thanks a lot, Andreas. So one thing I may have just missed that this estimation of the volume coherence, what's the performance of that and how does that propagate like error-wise in the estimation, as this is sort of the basis for this density agnostic estimation, you could say?
Yes, that's a good point. I mean, this is, if you look into the literature and look into how people are usually doing this, is considered the baseline way of doing this correction. But you're right, you potentially introduce additional errors by this, because you have to do an estimate of this coherence, so you introduce additional noise. By correcting it, you might also introduce biases. If you are in low coherence scenarios, if you have to estimate the coherence over very heterogeneous areas, you might introduce biases. That's also why I believe that, let's say, this potentially phase-only retrieval with two phases could be an interesting one. But exact numbers depend, I think, largely on the scene and the product resolutions that we will generate. But there is an impact on that.
Thanks a lot.
Okay, anything else? If not, we will move on to Mark again. Yeah. So this is Mark's own talk that he's going to be giving this time.
Yeah, the one I was mentioning before, don't expect too much of this one. Bear with me, just a second one. The topic now is a little bit different. And I don't know whether to say the title was too ambitious or not at all. Basically, we had in mind to show the way we understood that the database synchronization should be done for Harmony. But we changed the scope a little bit. Since we are basically involved in Harmony for the analysis of the synchronization subsystem of the system, then we try to provide an overview of the thing that we believe how the processing should work based on the evidences that we have from the different perspectives. So let's go into it. Very old slide. The situation is like this in bistatic SAR. We have basically a transmitter and receiver, both operating with their own oscillators. And instead of getting a signal like the one which is shown there, which is like typically an azimuth chirp with an antenna pattern, when we apply the realization of what the difference between the two clocks should look like, including phase deviations and a frequency, then we get a signal which deviates slightly or substantially from the ideal one that we're expecting. Now, when we process, then we see that instead of getting the response that we have here in red, then we get the response in blue. Nothing too dramatic because there is focusing there. Nothing too dramatic because the peaks are more or less similar. But we see, besides the problems of the side lobes, which are intrinsic and cannot be avoided in biostatics R, then we have basically a geolocation error or a deviation of the location of the targets. Now, what it looks like if we not only do we consider a single target, but the whole image, then the situation looks like this. Here I show the block diagram of the transmitter, the block diagram of the receiver, each with their own oscillators. Then here a little bit of math. Then this would be the instantaneous phase difference between the two signals, and then the apparent range history is perturbed by the signature of the clock. And basically we have that the geometry of the bistatic image is deformed with respect to its natural or its ideal geometry, no? And instead of having something like this black square, then we get something like more similar to this red flag. In which we have that this separation is proportional to the time as it is integrated by the evolution of this differential clock. If we take a look at one pixel, then we have basically that this pixel is deviated in azimuth in range, and then basically we have like a phase error. And on top of this, then there is this slight, it's slightly different thickness because there is this slight defocusing, but nothing substantial for the quality of the oscillators that we deal with in SAR. Good, fine. Now the situation in the case of harmony. There is a much smarter way to specify this, which is the one shown in the mission requirement document. But grosso modo, the situation for the three main different, let's say, observation scenarios or interferometric scenarios that we have in harmony. Anything which is not interferometric, since I told you that the impact on the radiometry was going to be small, then we don't care about it. For the stacks, repeat pass interferometry, we can tolerate errors around 10 degrees or even more, because if we're interested in the formations, then whatever happens on the single images, in principle, it's not too worrying. For the single pass interferometry, the talk, and other applications, the white spot altimetry also, then we would want to be in the order of 1 degree. And for the along track interferometry single pass, then there the situation is more relaxed because basically we're doing interferometry with the same platform. So we see that the driver is basically this one in the middle, the others to be kept in mind. Now let's move on a little bit more to complement the picture. The situation in harmony is like this, although the spacecraft are not the proper ones, and although this here I'm showing a transmitter, but the situation is picture yourself that those two satellites are the harmony ones. Here we have basically the radar receiver, here we have the GNSS, and basically we have that the same oscillator for one platform is driving both at the same time the navigation receiver and the radar itself. And this happens in the two. This also happens, this is the navigation receiver, this also happens in the guy, not in the picture, which is Sentinel-1, also happens the same. And like this, we expect to transform this problem of synchronization of the radar data by assuming linearity here between the signatures that we will see in the navigation receiver and the radar receiver, that we expect to transform it into a problem of calibration, no? Of internal calibration. Now, relevant elements here. This subsystem is identical between the harmonies, but it's not identical with Sentinel-1. Boundaries. The quality of this measurement is, like everything in this world, bounded by thermal noise. Increasing along track baselines worsen the differential GNSS estimates, meaning worse baselines in principle will affect our synchronization estimates. Ionospheric perturbations might affect us too, and multipath might affect us also. And a couple of observations based on what we know for the moment. The error is currently not dominated by thermal noise, but dominated by a mysterious signature of the GNSS receiver, which is more than 1 order of magnitude higher than the one that we expect from the thermal noise. And I say mysterious because I have a reason to believe that we can get better than what we already have, because we don't have currently an hypothesis to explain this situation. And the second thing which is relevant here is that the navigation-induced ramps, those coming from the baseline errors, in close formation, they account for more or less 5 degrees in 120 seconds, something like this, based on our current estimates. Good. This is the thing that we know in principle, the scenario in which we might have trouble making it work, and the scenario in which more or less we will have these residuals coming. Now, at least from our side, because as I say, this is precisely our role in the harmony system activity. Is that we put the focus in reducing via processing the contribution of the GNSS receiver to close to that we expect from the thermal noise. And as I'm saying, I mean, this is not wishful thinking. I have a reason to believe that we will manage to get better than we already have. And the other one is these navigation-induced ramps. They need to be kept in mind when the PVD processing is going to be defined. No? So maybe we have to consider longer data chunks or something like this. But these two things we have in mind. So in principle, these two numbers that we have here, I have a reason to believe that we can get better than this. Good. Now coming back to the database thing, which was in the title. The baseline is that this GNSS-based sync is applied, or this estimation, which will be provided by the GNSS-based, will always be applied in the processing, unless we are in a GNSS-denied scenario or a non-useful scenario. We have strong turbulences in the ionosphere, or we have data contaminated by the multipath. Now, I'm getting there. Now, the situation coming back to the products, then the situation gets significantly better than what I thought at the beginning. So basically, we have here for a single pass interferometry, repeat pass interferometry in oceans. And we have here the GNSS, the current best estimate, and the best estimate that I think we can get. And basically, the products which are affected, and then the comments which are explaining to some extent these phases that I'm putting here. So basically, if we get better budgets from the GNSS, which is the current work, then the residuals we might get to points in which the errors will be quasi-linear or even harmonic for very long data takes. Meaning, do we need database synchronization? Yes, we still need database synchronization. But if we are in a situation like this, then the situation can be relaxed enormously. For the RPI, here the situation is a little bit more open, because we don't know what is how this difference in the subsystem in Sentinel-1 is going to behave. We don't have any measurements so far, and probably we will not have any until it's flying. Therefore, remains to be seen what is the need for doing this. Please keep in mind that in terms of requirement, probably we can tolerate a little bit better deviations than this. For the oceans is what I was telling you at the beginning. We probably don't care about radiometric biases. Residual geolocation, we can tolerate probably also too, because we work with multi-loop products. So basically, I don't expect to see here major problems. Now, coming back to what is the thing that I was mentioning here? Here is this star here is, yes, we need database, but maybe not what everybody has in mind, no? And what does everybody have in mind? Basically, to use multi-squint for doing this. Coming back from the formation of the image. This is the old version that I had, in which basically the multi-squint was used here, and then I had an additional element here in which I was using these drifts in range of the images to bound the random walks from the multi-squint estimates. And with this, at the time of TandemX, and we showed like a couple of times that we managed to get consistent results compared to the results that we were getting from the dedicated synchronization subsystem. An example coming back from the same simulations that I was showing before, in which basically this was exactly the one shown. Sorry. Shown before with the three realizations of the oscillator errors, and then by applying the estimation based on the azimuth drifts, then we immediately see this is not tuned, so there still remains some tuning to be done, but we immediately see that we follow the errors pretty well. Now, coming back to the table again, we can make like a bold statement regarding what our expectation about the need for this database synchronization is going to be, in the sense that, as I was telling you before, if the GNSS sync works as it should, probably we can simplify the approach for the residual calibration, and we can enhance enormously the averaging blocks that we do for this estimation. Meaning we could even go for either with drifts or even with a phase. We could compare over large areas. If we know that our errors are going to be quasi-linear or even harmonic, then we could really simplify the database algorithm with respect to what we have in mind at the moment. If we cannot, then yes, for sure, we have to go for the classical solution or something similar. In the case of the RPI, this in any case, since a dedicated algorithm needs to be incorporated more like something in the direction of what Stefano is doing with the tomographic acquisitions should be thought of. Now, there is another problem with respect to what we had during the days of TandemX, in which this was used for a demonstration. And the problem is that all synchronization cases in Harmony are always differential. They are always between bistatic images. Unlike in the case of TandemX, in which we were basically synchronizing with the monostatic, which we knew that didn't have any synchronization errors. And this poses a fundamental problem, no? And it's the same problem of the original multi-squint, and how can we separate the contributions that we estimate? If we are making a differential estimation, how can we know what part of the error is attributed to which image? Which means that even if we get clean interferograms, they might still be distorted from the positioning, which might cause problems afterwards. Plus, we have the question whether we should correct the co-SLCs with this estimation or not, because we don't really know what part of the error goes to which image, no? So because of the problems above, we do need a way to estimate this in an absolute manner. And for doing this in an absolute manner, since we cannot rely on doing a coherent estimation with Sentinel-1, we could try to make a non-coherent one, but this is not going to get us anywhere near to the performance that we want in the case of Harmony. So what we are suggesting is to use an approach that we suggested like a couple of years already thinking of Harmony, which is basically using the channels in azimuth of each of the receivers. It's basically, this is the signal coming from Sentinel-1, this would be Harmony and its 3 channels, and then basically the fact that we have these small baselines and the fact that the baselines in a long track, we have basically mainly along track baselines, and this results in very small cross-track baselines. We can have, they are almost simultaneous, and we can even have correlation at raw data level. And basically what we're doing is the sampling for different channels of also is the same, like in the case of the classical autosync. It's just sampling the derivative of the error. And the suggestion, and this is robust, as I'm saying, because we are not, in principle, we are not relying on process data, and therefore we can get even more sensitive to, or more insensitive to geometric errors. And also, as I say, because this gives us a way to bound whatever differential estimation we make, then we run it through this estimation, and then this gives us a way to bound for the error that we allocate for the single acquisition, which allows us to make the alignment of the data properly, and then allows us to make the correction of the co-SLCs also. So the data flow runs like this. Basically, it's at the same time using the channel. So it's basically there is a bulk co-registration of everything. We make all the combinations for the 3 channels, which is basically this 3 times 2 divided by 2. So 3. Averaging and then inversion, and the inversion is basically it's basically directly an integration. Yeah, and a couple of things I was mentioning before, which is basically and then the suggestion is to integrate basically all the information together before we go into the estimation of the individual contributions. Good, and I think that is everything. Okay, yeah. It's not working, I think. Yeah.
Thank you very much, Mark. Does anyone have any questions for Mark?
I do.
Yeah, go ahead.
In the last thing, you're assuming that the errors that you see between the 2 phase centers or 3 phase centers, that they are given by the drift of the clock, which is true. But you're also phase errors due to phase errors. So the instrument has little phase errors. There will be an attitude uncertainty that will introduce a phase, and this will integrate too. So how do you separate?
But basically, by applying all the calibration that you can before going into the estimation. So you apply the internal calibration. You hope that your internal calibration gets rid of the instrument component, which is to some extent reasonable, because you have other. It's not the only thing that we will use. In principle, it's something which comes into the picture with something else. So which comes with the GNSS. But okay, this is mostly or also thought for those cases in which the GNSS doesn't work, no? Because in the other cases, for the cases in which we have like strong frequency errors between the two, then we believe that the propagation of the geometric errors in the conventional data-based approaches will not invalidate the approach, for sure not, but will complicate the estimation. So it's good to have like this support. Yeah. No, for sure. I mean, there is residual calibration to be made. Yeah, instrument is one. Yeah, as you say, attitude is also one. Yeah, it's true. But it's nothing that you don't have to do if you want to use your ATI interferometer. So it's something which is in line with the plan for everything. Yeah, we are aware of this, and this is.
Now Stefano could inspire.
Yeah.
Hi, Mark. So, if I can bring some experience from biomass, this last method is based on single images.
Yeah.
So, at the end of the day, it's an autofocus in disguise, basically.
Yeah.
I think it's gonna work to correct some, let's say, very slow varying trends. But now I am not aware of the actual behavior of the clock errors. Maybe it just works, but maybe it doesn't provide the accuracy that you need for interferometry. I mean, it's okay at the level of single images, but interferometry is way more sensitive.
No, this is understood. Yeah.
Go ahead. But the approach for biomass is that, okay, maybe an image is a bit defocused because of the ionosphere. We don't really care, because what is important is that when we have a stack, we defocus all the images in the same way. And so at this point, even if focusing is not perfect, but with interferometric processing, then it can be non-perfect in the same way for every pass. And this enables interferometry. So maybe this is a good approach for harmony too.
This is understood, and this is in line with the generic approach, which is on the table. I'm not saying we're going to substitute this approach for this one. I'm just saying that this approach solves the problem of having to assign differential components. So when you make a differential estimation, precisely to the individual images, which to some extent solves the problem of providing database calibrated images itself, even if they are not interferograms. And then it also solves the problem of residual geolocation errors which remain into the interferograms, which in the case of a mission, I mean, it's not the same. I understand the point, but if you have like a campaign of data which you're going to use to train algorithms or to validate algorithms, then is one thing. If you have products for a mission, then you want your products to be. So it's more thought to come on top of what is already on the table, and to be able to make the whole story a little bit more robust. Also considering the cases in which the GNSS base might fail, and that's the whole thing. Good.
Okay. Then unless you have any other comments? No? Yeah. We should close this session and start the next bit, which is the round table for this session. Yeah, so thank you very much, Mark. I think so, yes. Yeah, okay. So the round table is not supposed to officially start for another 12 minutes, but I don't think there's any point in sitting here in silence, so let's just move straight on. So this is where we get to give some recommendations. We have a few seed questions, but as this is, at the end of the day, basically a harmony session, we're really looking for feedback from the community on what we've presented, both in Paco's talk earlier in this week and here today.
Hi, I raised this yesterday, but I think it's important to raise it again. It's around the sort of the coverage for the DEM, the XTI portion of the Harmony mission, and specific. I think it reflects this community. We're focusing on straining regions and volcanic regions, but the other and more common hazard is the landslides, and they happen not just on volcanoes, as you know very well. So, could we make a slightly different recommendation? Instead of just focusing on those volcanic straining areas, include also all areas with 10-degree slopes, more than 10-degree slope, because that would really, really help us.
Yeah, so we've
build those
certainly
models.
thought about this for TDV, and for TDV we have the tectonic strain mask, so we should be getting, which covers most of the areas with slopes of greater than 10 degrees, because there's a feedback there. So we should be getting three-dimensional velocities for landslides, most of them at least.
It's the elevation model.
It's the elevation model at which...
And there are large parts in your mask I saw there already, the mists, West Africa, for example.
Yes.
That would be really helpful.
That is currently not in the mask. We should think about that. Yeah, that's a good recommendation.
You have to be aware in the end that so landslides often are small, I guess, and they're very scattered. And we
but
have,
the big science problem we don't have a good handle on is the volume frequency distribution for landslides, and partly because we don't have the DEMs available in the world in the before-after phase to do that. And that really does help us build those scenario-based or even hazard models more accurately. And it is the most common and most costly geohazard on any 1 year around the world.
I think the exercise for you is to, not for us, it's for you, to send us your desired mask. And then we will incorporate it in the discussions we have in the mission advisory group. And then we will see how much, what is the implication. So we generate lots of data, which is the limit. So we cannot cover everything all the time because we cannot handle the data. But yeah, send us your wishes, and then we will try to make you happy.
Iqbal again. Hi.
Sorry, I had a second point. I was just waiting. It's more around how much time the satellites will spend in XTI mode versus by static mode, because as you correctly said, Julia, that's sort of the quick response type. Getting the pre and post is quite valuable, not just for volcanoes, but also for any deformation process.
It'll start to erode pretty quickly, yeah.
And is there sort of a plan on how much time it spends for each year or for part of the mission, or whatever they've got for that?
Well, this is Paco's plan, but I can say briefly. So the current plan is that the first year will be XTI, and the 5th year will be XTI, so every 12 days during those 2 one-year campaigns. In between, there is some flexibility to move back to XTI. We're still working out exactly the details of how often that will be possible. There's quite a few implications on fuel budgets and things. So we don't quite know how many times that will happen. But definitely during that first year and the 5th year, bearing in mind this is a science mission, not a monitoring mission, we should get 12 days wherever we choose.
So, Juliet, on the third point, when you say global, you mean just within your mask? Or?
This is Paco's point. What did you mean exactly? Global
could cover, so depending, you are limited by the acquisition plan of Sentinel-1, so maybe it's impossible because our Sentinel-1 may not cover everything, but in terms of capabilities, so in a month you would have covered the entire globe a couple of times if you wanted. So and it's not a lot of data, so if there is enough people asking for it, then we could push for it. And for me it makes sense to have a base map DM. There's also a gap, because we have now time series of DMs generated by TerraSAR-X, but now TerraSAR-X, so TandemX will stop at some point. And then there are plans for follow-up missions, but there is also a time where there are not, and we have seen that there is a value in having a time series, so updated DMs every year or something like this. So for me, there is value in that, but if I just say it myself, I will be ignored. If lots of people ask for it, then maybe not.
Yeah, I think, Paco, this would help us answer Iqbal's question as well. If we have a global reference DM, if there's a large earthquake or large landslides, hopefully we will have enough flexibility to get the after one as well.
Yeah, I would. That's exactly the point I was going to make, that if you do respond to places that were outside your original science focus, then a base DEM might be valuable.
Tim?
Yeah, I don't know how many people you want to say agree with that strongly, but I agree with that strongly. Having a base DM, each of your phases, actually having one in the first phase and one in the second phase, then you can do differencing, and that will help. Ekbal's thing will help you respond to other events. So I imagine there wouldn't be anybody in the room who would disagree with that, but maybe you can write down there was strong agreement that this should be a high priority.
Yeah. Can we have a show of hands? Who agrees?
There we go.
Yeah, everybody agrees. Good. Is that a strong enough backing?
We will write it up as an extremely strong request by the community. And since there is nobody from ESA in the room, they will not notice.
Yes, I was wondering whether we could use the DEM from Harmony to get the geolocation of PS and DS points for Sentinel time series. I think it would be really useful because geolocation of Sentinel, PS and DS points is quite off. I'm not sure. I think for DS it should be possible. PS is maybe difficult because of the different angles, but...
I think you answered your own question.
Oh.
So I think I agree. I don't know.
Yeah, I'm not sure the DM heights themselves, the derived heights, would be accurate enough.
Better than not having it, no?
Yeah.
Andy has an opinion.
Oh, Andy, sorry.
And he needs a mic.
Thanks. Yeah, I think you did answer your own question, but I think for PS it's more difficult, right? Because the DM won't be made at full resolution. Yeah. So that's the issue.
Yeah, plus, the PSs will be different. So the PSs are directive of most of them, right? So you will the permanent scatters that you see in Sentinel-1 are not the same ones that you see in Harmony, which is a nice thing, because that means that for some things you get complementary targets. But assuming that you're seeing the same is not necessarily. No, mostly I think not.
Or the XTI phase should fly closer to Sentinel-1 satellite.
That's a no-go.
Okay, clear.
Stefano.
Thank you very much. So now about the DEM. So I want to quote a poster from Airbus, which was on display on Tuesday. The DEM is super useful for water and land use management, civil engineering, insurance and disaster mitigation, ecological monitoring, defense and access security. And these guys are investing. So I think that the third question is yes, of course. so there's no question it is useful. Every mission that has the opportunity to generate a DEM does it. Biomass does it. TandemX did it. And of course, Harmony has to do it. It would be super, super useful for me. That's...
Okay, we will upgrade our recommendation even further to extremely super, super useful. Yes, thank you. That's great.
And then, since I'm speaking, if I can go back to the first question. Yes, there are outstanding science questions that need multistatic radar system, let alone displacement for a number of applications like forestry, snow, ice, maybe tomorrow desert, I don't know. We are trying to do in a repeat pass fashion what we should do in a single pass fashion. And TandemX or Lutan, by the way, are wonderful examples about it. If you have a cross-track interferometer that is simultaneous, then you get rid of all the complications due to changing weather conditions, changing snow condition, changing ice condition. And so you can decouple time and space. And this is super, super. It would answer right away all the questions that we are starting to ask now with biomass about all the water changes within the forest structure, or for snow. What if the composition of the snow changes because one day is hotter than the other day? So, and then of course, we also have the north-south component. Okay, this is not a new question, but it's super important, and you just demonstrated this earlier on this morning. So my take for question number one is that every mission, every explorer at least, should always have an Harmony-like configuration. So with two, at least two.
Okay, that's a great recommendation. Every mission should have companions.
Right.
Yes, perfect. Actually, I'm not a forestry person, so I'm going to ask a naive question. Could those questions be addressed with Harmony, or do they need a different mission, a different multi-static mission?
Well, Harmony has phases, and it's C-band. C-band is not as cool as P-band, but okay, that's... No one is perfect, so it's okay. No, jokes apart. Harmony is a C-band mission. It has phases, so it cannot do a cross track and the long track at the same time. It would be wonderful if it could, systematically, but of course it is an explorer, so it's perfect for an explorer. If we could play the same game at L-band, for example, this would enable different applications, so probably something more accurate for forestry because of the penetration, because of the sensitivity to the scattering of the terrain below the vegetation, or for interferometry, for ensuring a higher coherence in a vegetated area.
Okay. The companions for L-band missions specifically. Yeah. Cool. Thank you.
L-band Harmony.
Rose Harmony. Anything else? Should we wrap up?
So we can wrap up, or you can come with your random comments and opinions, which is the purpose of a round table. It's not really us coming up with shit questions are supposed to provoke debate, not to be the debate. But if...
John?
Thank you. I don't like the ionosphere, so we try and get rid of it. The whole point of this is the troposphere doesn't matter because you're piercing the sort of same state. But with the ionosphere being higher, is the separation wide enough to look at really short wavelength differences in the ionosphere, particularly at high latitude ascending? Because the piercing points are a bit further apart.
So the question is if the ionosphere, so the troposphere we get rid of, the ionosphere, if we get rid of it? I'm going to say no, but there are people in the room who can say no or yes with better, I don't know if Andy or...
Yeah. We're all looking at Andy here, sorry. Oh, Andy says no, if anyone couldn't hear that, but he's going to give you a more detail.
The question is, can we learn from the ionosphere? Then the question is yes, I think. But it's a pain for us if we're trying to measure deformation. Yeah. So we can't get rid of it.
But for the ionosphere, we are dependent in the end on the normal ways of getting rid of the ionosphere. So we have to do split spectrum, etc., no?
Yeah. I think we can do a little bit better, right? But
yeah. Are you already spoken?
No. I was just thinking that every time there is a discussion on multistatic system, we always end up with this recommendation that we know nothing about multistatic polarimetry. And we still do not know anything, or I don't at least, so maybe it's not stupid to restate this commentary.
I agree with this. There is, I will say a couple of things. I will say just one sentence about this. We know something because we have looked into it a bit. Although we've had more times for questions and I had felt like torturing people, I would have asked him in this presentation, what polarization are you using? Because there was no polarization in the slides. That we are sort of assuming, and I see a lot of work that we do is sort of assume that we are in a VV world, which is wrong. There is no VV when you go bistatic. So we have to pay, and this is maybe a warning for everybody. Polarimetry in bistatic is not like bistatic, like monostatic. You have to stop saying V and H because they are totally wrong polarizations to think in. So there is a lot of work to be there, and we know a bit, but we know only a bit. So this is indeed going to be a big science question. What do we see bistatically? So we know we see different things, and we need a different language too. So it's a good point, and maybe in next Fringe there will be more on polarimetry in the discussions of harmony and in other workshops as well, but it's a very important point, yes. If you want to go for coffee, we go for coffee. We can do it democratically. Who wants to go for coffee?
Okay. Well, thank you, everybody, and thank you to all the speakers again.
Very good. Dr. Dix, Professor Dix. Very good. Doctor or Professor.
fighting over it.
Yes.
So there's how many sessions are there to present? I guess we do it.
17 sessions.
How long are you giving people?
Well, how much is 17 times? I don't think they will take
Yeah, I think maybe don't allow any
Oh, wow, yeah, no, because actually there's no time, 10 minutes.
Yeah, 10 minutes. Yeah, it's got to
I don't know how they can keep it with 17.
Yeah, I mean, that seems too many, doesn't it? There weren't 17 themes. Maybe that includes like Earthquakes 1, Earthquakes 2. Yeah.
Well, the info is compliant.
Okay.
Aula is bringing the list to the order.
Yeah. How many?
16. So many sessions.
Yes, a very professional handwritten program.
So, and we.
So instructions. This is the order.
There is
Each 12 one has got 7.30. 7 minutes, 30 seconds.
but this, for example, Uno doesn't have anything. It's just one slide.
So
So
it might be
you're gaining some minutes.
Why don't you tell people 5 minutes? Because,
Yeah, 5 minutes, and
because
then there
they'll
is
run
something
over,
there
yeah.
for.
you're the
Anyway, Aula will be here. I'm going there to the technician. So if someone changes an order or says, I want to present this instead of that,
I'll check
I will.
the time to use slides.
Yeah, exactly. Have a look. You can delete, cancel, add.
No, just don't forget anything.
We should, yes.
I'm going upstairs. I'm going upstairs.
Can we start on time?
I think you should.
We should. 2 minutes. 2 minutes.
Just like
Middle. 4:10. Okay. Marcos, if anything happens, if anything is you want to write me before now. I'll be there up, okay? 5 minutes and then cut it. No, because we did it now, you know. Like, it's more or less in the order of how they went.
Hey, I think it's bad for the people. They don't know when.
I wasn't aware it was yeah, sure. I'll let you do the talk.
Yeah, sure.
Okay, please take your seats, and we are almost at the end of the workshop. We need to start the summary sessions in 2 minutes. So the way this is going to run, we don't have a strict order for the presentations. We go roughly in the order that they were, like Monday, Tuesday, Wednesday, etc. So the first one is Sentinel-1, and then it goes to theory, etc. And we go on from there. I'll ask for the presenters to come up in the front row. We have roughly 5-6 minutes per summaries. We have 16 in total. So there is not really time for discussion. So if you find during the summary sessions, you find something that absolutely deserves to be said, please email the chair people, and we can get those recommendations still in. So without further ado, Nuno, you're the first one. So the Sentinel-1 session slides should come up.
Yeah, so our Sentinel-1 session was pretty different from the other sessions, because I understand. Yeah, because it was following basically the opening session, and we are not having any kind of discussion and seat questions to present. So I can look into that. So we have a 5 presentation on the Sentinel-1 mission that cover the mission status and also cover the performance of the current satellites. We have also seen INSAR results from the Sentinel-1C and Sentinel-1D in-orbit commissioning phase, data that you are now using systematically. We have also seen a presentation from Mario that have shown some results of the ATI experiment that we did, mostly in preparation for Sentinel-1 next generation. And the last presentation from Thomas addressed the exploitation of Sentinel-1CD tandem, one-day tandem over Antarctica. So during the discussion, together with Dirk, we grabbed 2 recommendations. One was to, so we present the fact that we're going to start next year. We intend to start a reprocessing of the mission that will deliver products in the ZAR format, and I invite you to look into that. And one of the recommendations was to assess if it was possible to provide extra wide SLC in certain areas. So we still have to define what are these areas. So if you have recommendation here on what are the areas that we need to generate into extra wide SLC, just let us know. We'll look into that. And another recommendation or that was placed in this session, but also later on in the other session, was to to assess the possibility to repeat this one-day experiment if the opportunity occurs in the future, for example, at the occasion of commissioning phases like we did for Sentinel-1C and D. So that was it for us. There was, as I mentioned, there were no seat questions, so there is no specific accommodation based on situations that we have. So if you have any questions or remarks.
We save those for later via email.
Exactly.
People have to catch their flights. So the next one would be theory and methodology, and the one after that is ESASAR future missions.
Okay, thank you. Yeah, this was the first session after the Sentinel-1, so it was a plenary session. I guess most of you have been there, so I don't need to repeat that much. If you would like to summarize it, it was about next generation INSAR methodologies to extract richer geophysical information from SAR data using advanced modeling, geometry, wavelength polarization, augmenting conventional INSAR with additional information, so the time dynamics, wavelength diversity, geometric diversity, polarimetric diversity, processing innovations to obtain more accurate or more interpretable and more application-relevant deformation measurements. This is basically the statement on the overall thing. We made a very short summary of the different talks that were given, but I think since everybody was here, I think I don't need to go over these ones. These were the presentations. I picked a couple of posters that were really into new technology, but I guess most of you have seen this. So, conclusions. Theory and methodology has been developed to extract richer geophysical information from SAR data through advanced modeling, geometry, wavelength polarization. Conventional INSAR is augmented with additional information, so basically the things that I started with. So I have a couple of recommendations. First is that in our view, this is the first time that we heard anything about space-to-space RFI, from, for example, GAUFEN3 to Sentinel-1. I also heard that it was the other way around, that GAUFEN3 has RFI from Sentinel-1. So that is apparently a thing that is coming up. There are also geosynchronous missions coming up, which are illuminating continental scale areas near continuously. And although we know that the power densities are probably way too low, I think it is good if ESA would systematically investigate this and report the impact of space-to-space RFI, particularly for geosynchronous missions. And particularly on the surfaces from Sentinel-1 and Sentinel-1 next generation, just to get that out of the way. If necessary, take mitigating measures and then report back to the scientific and the operational community. The second one is on convoy mode. So we considered the fact that currently the main challenges in INSAR are related to the interpretation of the signal, or the origin of the signal, whether that is ionosphere or phase closure or penetration into the ground. And we consider that C-band and L-band interferometric observations show quite different signals under different circumstances for distributed scatterers. And that the option of a 1-minute separation between Sentinel-1 next generation and Roselle acquisitions from the same viewing geometry, and this convoy mode was presented during this Fringe. The expectation that point scatterers from convoy mode acquisitions in the built environment will most likely overlap largely, which would greatly improve phase ambiguity resolution, so the unwrapping and scatterer interpretation, geolocation of all those billions of points that we have. The fact that ionospheric errors can be eliminated fantastically if you would have such a wide bandwidth between C-band and L-band, because you can assume that the ionosphere is nearly identical, similar to the troposphere, but there it will not help that much. And that then, depending on what the final thing will be with Sentinel-1 next generation, whether that is really going to wide swath, so that would mean that already we would have more temporal sampling. We recommend ESA to consider the 1-minute convoy mode to be used as a default land mode, but I heard in the discussions that there are different opinions about this in the community. So basically, the most important thing is the recommendation to further investigate different scenarios on the use of the 1-minute convoy mode. And one option would be to investigate NISAR, which has already simultaneous L and S-band observations, and as soon as these become available, we can actually have data which are from different wavelengths and are simultaneous. So we will learn from that, and then to report this back to the scientific and operational community. The final recommendation is about INSAR trust and confidence. So we considered that the increasing availability of INSAR data, processing tools, analysis-ready data, products and services enables a growing and increasingly diverse community, including non-experts, to generate INSAR information products, such as in the scientific publications, but also operational data products. And differing methodologies and assumptions may lead to contradictory results, and potentially this reduces the trust and the confidence in INSAR-derived information among a various range of stakeholders. And trust and confidence are essential prerequisites for the broader adoption, impact, and the continued innovation of INSAR technology. And currently we don't have any broadly accepted framework for assessing, communicating, and strengthening trust and confidence in INSAR information products. Other geodetic techniques, including GNSS, have undergone similar maturation processes and have developed mechanisms to establish community-wide confidence in their products. So considering all this, we recommend that ESA would support an initiative that was made by the International Association of Geodesy, IAG, and the GGOS, part of that, to establish a special study group on INSAR trust and confidence, with the objective to investigate effective approaches for building trust and confidence in INSAR information products, identify lessons learned from other geodetic techniques, disciplines, Earth observation disciplines, to consider the needs and expectations of different stakeholder groups, including science, governmental, commercial, public users, and to develop recommendations and best practices for the assessment, communication, improvement of trust and confidence in INSAR products and services, and recommends that that special study group report the finding back to the next workshop. And ideally, this would be something that would be, it would be great if ESA would support this initiative, but it would be nice if for example, NASA or CEOS or other international organizations would also support something like this. So that's it. Thank you very much.
Thank you, Ramon. The next one would be ESA Future Submissions, and the one following that is phase closure.
Okay, yeah, I think we were the last plenary session that day, and I also have it like very short. So we had, or the objective of the session was to give the latest overview and update on the SAR missions currently under development in ESA, including mission concepts. So we had a presentation on ROSEL, we had a presentation on Sentinel-1 Next Generation, so covering the Copernicus missions. Then we had one on Harmony and another one on Earth Explorer 12 candidate HydroTerra Plus. We only have one seat question discussed during the roundtable, which was which gaps remain open and are not addressed by the current developments. And we got like some feedback, including like I have like recommendations and questions here together. So one, how scientists can be involved in CARVAL activities of ROSEL and ESA missions in general. That this should be like an open process. The other question is on how ESA will handle the growing amount of data in terms of archiving, data retention, and data uptake. Then one based on industry and services. This was a recommendation given that they need sufficient time to react to new data, also data volumes that came mainly from what I presented on ROSEL. So, and that ESA is asked to provide data and samples and formats early so that users can prepare in advance that the services are ready to take the data up in their services once they become available operationally. And then also we had C and L-band in a convoy discussion, and that it would help ionospheric distortions. And I'm personally very happy that we got the stone rolling here about the spacing of Sentinel-1 and ROSEL, because it will be one of the questions we have to deal with in the near future. That was it. Thank you.
Quick questions, remarks? If not, we move.
Yes, next one is phase closure, and after that, atmosphere and ionosphere. Okay. So you're doing both, all three.
Hopefully with help from other people who were there. All right. Where do I push? The green.
There. Try this one. This one.
All right. Just to quickly summarize, the talks in the session were really showcasing the fact that the amount of data that one can use to evaluate soil moisture effects through phase misclosure, vegetation effects, all of that has greatly increased. This is both through the data that's available through spaceborne platforms, airborne platforms, and even tower observations, that we're more and more frequently able to access multiple wavelength data, and that polarimetry is increasingly becoming possible. There were several presentations that showed multi-year phase closure results, deformation results in areas with significant amounts of agriculture, where through the use of other ancillary data, people are able to separate out the effect of individual crop types and how they vary across the phenological cycle. And this has really highlighted the growing need to separate out the effects of displacement itself from the effects of soil and vegetation water content, especially in places where mining of groundwater is increasing and these resources are getting sparser. And so apart from just trying to mitigate the effects on studies of displacement, there's also a steadily emerging number of applications that are very interested in the soil moisture or vegetation properties themselves. So in recommendations that came from various people who commented, there were comments that basically the data is now mature enough that there really is time to increase the focus on trying to understand and model and develop algorithms that can treat the various aspects of the phase misclosure issues, particularly outside of bare soil regions where there's also the effect of vegetation. We need to improve our understanding of those contributions, both to coherence, phase shifts, the overall phase shift associated with vegetation, and the closure phase. And that modeling of the data needs to be obviously accompanied by constraints on real-world data rather than pure modeling, and that any successful model should try to explain all of the different dimensions that we see in the SAR data, including backscatter as well as the phase misclosure. And separation of all of these effects may benefit from increased availability of polarimetry and multi-frequency experiments wherever available. And so the hope was that more of these coordinated data acquisitions could occur in the future. Another comment that relates to some of the things that were discussed the previous day about the wider community was just that there continues to be a growing understanding of phase misclosure within the community, but it's not universal. And so there could be various ways to attack this, either from providing more training materials, like is done for many other aspects of differential INSAR, that help to introduce people to what sort of statistical properties in the phase will introduce these effects, and just increasing the clarity of language that people use when we're discussing, say, the overall phase shift associated with vegetation change from the phase misclosure itself, which is more related to the statistics of the signal. And that, like in many other areas I've discussed during this meeting, quantifying the uncertainties both on the observed phase effects, but also any eventual modeling of them is really critical. I think that was it. Shift to the next one.
Okay, great. Yes, so next one we need number 5, atmosphere and ionosphere.
And I want to qualify that I was not here for the entire session, so please anyone else who was there can either send comments afterwards. All right, this was mostly from Michael and David put together these slides. And so here again, in this particular session, the objective was primarily reducing the effects of the atmosphere and ionosphere on INSAR. And there were presentations on software tools, methods, and the increasing availability of mitigation approaches for the atmospheric and ionospheric phase screens. And a lot of focus on operationalizing and increasing access to these tools. So Opera showed results of their three-dimensional products with different layers in the troposphere that can be used for any type of SAR mission. There was a study showing how low-cost GNS receivers can be deployed in very dense networks to provide targeted studies in specific locations. And then on the ionosphere side, there were both studies showing that neural networks show some, promise in providing robust estimates of these phase screens, but that also split spectrum algorithms still need further work. And there was also some results presented about how the interpolations that are necessary with any of these numerical weather models can also introduce their own effects that need to be carefully characterized when these results are presented. I'm losing my voice. Excuse me. And so the recommendations were to, for many studies, simplify access to these multi-frequency data sets wherever available. These can help separate out the effects of what's going on with the dielectric constant on the ground versus what's going on in the troposphere. And that whatever ESA can do to follow up their previous successful efforts to facilitate access to non-ESA data sorts, S-band data, things like that, would be of great benefit to the community. And as all of these products are being developed and made available, it would also be helpful if SNAP could provide support to ingest these different formats for users. I'm sorry, I'm having trouble there. Oh yeah, and again with the publication theme that seems to hit many of these sessions, as these models are used more and more and people use them to look at smaller and more subtle signals, characterizing what correlations there are, spatial correlations and temporal correlations might be leaking into these results is, again, of critical importance. And, okay, so I was not here for many of these, but the recommendations were to encourage dual pole studies, to look at Faraday rotation correction approaches. And so with L-band data, this is clearly going to be very important. And there was a proposed idea to have more of these super sites where the different correction techniques for the ionosphere could be studied with multiple wavelengths, and including ground-based scatter radars as well. And then the recommendation that all of the troposphere products that were discussed earlier could actually be, we could look into how far back in time we could release those for earlier missions so that they could be used for longer-term studies. And I'm not sure, I was not there for the discussion of the last one, I'm sorry about that, but more SAR coordination meetings between agencies are also probably useful.
Okay,
thank you.
Thank you very much.
And the next one is INSA Products and Services, and the one after that, volcanoes.
Okay, this is the combined summary of the INSA product sessions and the one on operational services, because we had also one round table session, so we combined our summaries. On the INSA products, we had 5 oral presentations covering a range of different topics on ETAT, urgent response, dynamic DEM, and analysis-ready data products. And yeah, no time to go into detail here, but they all, of course, had a description of their product status and, importantly, future plans. And we have had, of course, also various associated posters on these topics. The next session was about the processing environments and the services. In this case, 6 presentations and posters covering, indeed, processing platforms, operational ground motion services, and other mass processing tools, both on interferometric processing and on further data analysis like anomaly detection. We had a roundtable, and to steer, or not to steer, but to help the discussion, we had 2 seat questions. And basically the recommendations and answers to these questions are on the last 2 slides. The first one was also linked to the information given on the first day regarding the Sentinel-1 mission and associated products. And the question was whether there were any final recommendations towards ESA regarding the plans to do a reprocessing of the data in 2027, and also to produce ETAT products for the data archive. And this would be the moment to maybe give some final recommendation for these products. So in general, the feedback was that the community very much appreciates this reprocessing, delivery in ZAR format for future high-performance application, and certainly also the generation of these ETAT products for the data archive. There was also some concern reflected by some users regarding the data volumes and the associated re-downloading of data and storage, etc. So also partly triggered, I think, by a comment given by Ingvar Larsson about releasing focusing software. There was the suggestion to make this or a type of processing software part of ESA's portfolio so that users can also do the L0 to L1 focusing step on their local premises, so to reduce the download and storage requirements. So this is by part of the community a demand. Of course, we would still like to have the SLC data as well. So something, recommendation to see what is possible towards ESA. And another remark was made on the community would appreciate to be a little bit more in advance, be let known about the plans and the planning of these kind of steps. Regarding, there was a second seed question that was going more into the RD data. And regarding what format and what processing settings. Also here, the feedback was that people are positive about having this additional product in the portfolio regarding co-registered SLCs. So that's certainly an interesting step, a good step forward. Of course, we would like to keep the existing data availability and data formats. But the community would like to be, and I, to be honest, don't know exactly how, but would like to be involved in the specifications of this product, so that we can, at the beginning, have an influence on how these co-registered SLCs will be configured, specified. So these were our, this was the feedback from our session. Thank you.
Thank you, Frick.
Okay, so next one, volcanoes, and after that, the future SAR missions.
Yeah, so there were, a number of talks on using INSAR and modeling, and talks on trying to derive a topographic change from especially radar imagery. And then also presentations on processing services that combine processing with anomaly detection, dynamic modeling, etc. So quite a variety, and we had a number of seed questions. And so the first one is, what is observationally missing to get some of the outstanding questions in volcano science? So, of course, a recurring theme in volcanoes is always temporal sampling. We had a great example from Piton de la Fournaise where they get, I can't remember how many passes per day, I think it might be, or per, they have something like 20 plus tracks that they cover them from different modes. So, I mean, that's an extreme case of what one would like, but certainly getting towards daily type or as short as possible sampling is obviously the desire. Another theme was that, right now there are some talks on using radar amplitude imagery to kind of back out topography change. And so in the future, of course, we heard talks, and we'll hear more about Harmony, but repeat topography is really important in volcanology since it has, there's often extreme topography change or simply things like lava flows or other kinds of flows changing the topography. And then finally, there's integrated data analysis. So we've heard from systems such as LIX, and where anomaly detection and modeling are getting increasingly integrated. And there's some question about whether for volcanoes, development of a quote-unquote digital twin is desirable. And I think, in general, we tend to do that in the volcano world. From volcano geodesy, we're using the data to constrain as best we can based on the strength of the data, the physics of the systems. But of course, a lot of power in constraining these models comes through the integration of other observations, such as thermal time series, gravity, seismic information. And so you really need a lot of that to get at the complexity of these systems. So I think digital twins are great, but it's really about the data. But from the geodesy side, temporal sampling will be one of the key things we can add to that. So the next question was, what are the needs for repeat topography? And again, as I mentioned, there are several examples in the session of using amplitude imagery. But of course, the second point is this really points to the need for dedicated topography mission. I think Harmony is going to go a long ways towards informing us about that, but since it's an Explorer mission, it's doing that on it has a plan that's not wall-to-wall topography change. But I think we'll learn a lot from that, and in the future, things like, it was mentioned, co-flyers with, say, Roselle came up in the Harmony session, but ways at getting at both topography, but also, for example, in volcanology, we really care about bare earth topography, and yet, so vegetation forests are a problem. And so if you can, for the volcano side, if you can remove that vegetation, that's the ideal, that would be ideal for us. So let's see, next one. Okay. There's a question about data continuity. Of course, we want data continuity. I think we're used to connecting time series from various satellites. We've been doing that over the years because for volcanology, there's the short-term, highly dynamic aspects, so where we want daily, sub-daily, whatever, very high temporal sampling. But increasingly, the richness from these long time series, decadal or decadal plus time series, is increasingly important for constraining kind of long-term dynamics of these systems. So I think that maintaining the same viewing geometry is good, but I don't think it's critical. And I think, of course, as we get more and more SAR missions flying at the same time, many of the data issues are kind of being, some of these issues are going away, but certainly continuity is important. And then there's a question about commercial satellite data. Of course, the challenge there is there's both access and, well, the first challenge is getting data acquired over the place that you want it, and the second is then getting access. And so the question is, getting data acquired, you may have cases such as Kilauea or Iceland or places that are kind of hot at the moment or typically very active, so there you get a lot of data potentially, but how can we get access to the data or task it in the case of changing situations on the ground? And so maybe Isa could
could get into that game a little bit like NASA already has a commercial satellite data program where they have data buys and agreements with companies. And so maybe something similar, ESA could do something similar and make those data available in some way. So, and there's also a question about the role of operational services. Of course, those are, you know, there things like opera are, of course, geographically limited. There's a lot of work with the Comet group, with LIX, where they're doing this more systematically. And so I think that's the future. I think one question is whether in some situations, and there was, Franz Mayer talked about the ASF capability that they've generated, but one question sometimes is, can researchers interact or get access to kind of on-demand processing? So that's another thing to consider. And so this question came up earlier in terms of S1 and rows L in terms of this kind of convoy or not, or spread formation. I think that the consensus was that the spread formation for volcanology would satisfy the most needs, although we were considering a one-day delta T between them as something that would be very good for more dynamic processes. The 1 minute separation, I think, aside from its ability to, of course, reduce errors from atmosphere or ionosphere, from a process point of view, yes, I think off the top of my head there would be cases where 1 minute could be useful, but probably 1 day would be a more, if you're going in a close, you know, a short temporal sampling mode, 1 day would probably be the better one for volcanology. But again, the spread 3-day formations probably would serve a broader community. And that's it. So.
Thank you, Paul. So the next ones are future SAR missions, and after that we go to displacements.
Okay, so our group was talking about future SAR missions that are not actually planned yet, but people hope to have. So because it was speculative, the discussion in the roundtable ended up being decidedly philosophical and somewhat speculative as well. So this is what we came up with. So we talked about geosynchronous SARs of various sorts, multi-satellite, small constellations with vector diversity in lower than polar orbits, and a number of other technological concepts. So out of these presentations, we came up with some seed questions for the roundtable, which occurred later in the day. And these were represented here. We saw a number of mission capabilities, and there was some motivation for them, obviously, but it wasn't really clear from the presentations, you know, what the driving applications or science was for them that would really lead to something substantially different. You know, these were short talks, so perhaps you can't go into great detail, but it left the question, you know, these things seem to be highly technology push-driven, not so much science-driven, which is okay. Many of the people in the discussion felt that was a good thing. But then the question is, how much better are these systems than what's already in the suite of international satellites and science-driven missions, and how does one quantify what better really means in that sense? And then the last question was, what is still missing to complete the fleet of space missions in terms of all the various things we care about, multi-frequency, coverage, polarization, line of sight diversity, and that kind of thing. This can be taken two ways, both, you know, what more do we want beyond what we already have, and do we really need all of these things? So here are a couple of observations that came out of the session. My co-chairs are not here. They left, so they left me to pose these things to you and get your feedback. The first one is that commercial satellite missions are showing sub-daily INSAR capability, but the community seems to be more this community seems to be more science-driven, and the commercial companies tend to be more, you know, product and profit-driven. So there's wonderful demonstrations of systems that exist, but are these systems really what we should necessarily be relying on to do our science in the future for the global kinds of problems that we are trying to address? Another observation is that the advances are triggered by lots of different modalities for the new generation sensors, but the methods and the workflows, according to the person who wrote this, which was not me, are using techniques that are fairly well established and are not being pushed forward in a sort of revolutionary way. It's all somewhat incremental in their opinion. So they wanted to pose the question, are all of these new missions with so much data being generated to some extent limiting our ability to innovate in the use of all these data? We have petabytes and petabytes of data from all these different systems that exist. Are we really taking advantage of all those data by really digging into new algorithms, new methodologies in order to really exploit them? And then if we actually did that, would we need all these other new missions that are coming along? Those were the questions that were posed. So these are not these are, of course, not recommendations to ESA yet, but from this discussion, somewhat philosophical, came some of specific recommendations. So it was felt that some of the things that we're doing in space maybe could be better explored in a more cost-effective way with more airborne campaigns and maybe even high-altitude platforms. And of course, these things are happening, but the question is, should we be doing even more of it? Some things are best done from space, of course. Turbulence in the atmosphere makes things difficult for a lot of our SAR-type observations, but perhaps more could be done in that area, be more cost-effective, and explore the space of vector diversity, polarization, multi-frequency more cost-effectively. And then maybe have a virtual constellation satellite concept that is a little bit more formalized that would allow us to really look at the international data sets beyond just super sites, which of course we all have, but looking at the actual coordination of all of the different missions in order to really take advantage of data and close gaps for the international community in the future. Then there was a suggestion that ESA might consider developing a new program that is somewhat in between the Scout program, which is quite low cost and difficult to do a SAR mission within its context, and the Explorer program, which is a much more substantial program, but maybe there aren't so many of them because it takes so long to build any one of them. That might allow for some of these, not microsats, but sort of mini-sats with substantial SAR systems to be able to do some of these things. If you can't do it in airborne and you want to do it in spaceborne, and it's essential to do it in spaceborne, this might be a better platform to do it within the ESA framework. And then the next one here is that this technology push versus science pull needs to be carefully crafted. I'm sure we all think that we're doing it well, but I guess the consensus was a conscious effort to understand technology push versus science pull is important. there is a sense that, of course, we want more capability, and commercial systems are being thought to be a pathway to doing that cost effectively and cheaply. But I think there's a tendency, at least in some agencies, I'll say my agency, to think that commercial systems can do everything, and that the recommendation here is that ESA drive what is done with commercial systems in terms of capability, as opposed to letting essentially the commercial systems drive that. Because commercial systems generally do need to make a profit, and science isn't always profitable. Thank you.
Thank you very much. Is there, one quick comment, question? So thank you very much, Paul. I pretty like your provocative statement. So I think we move to the next session, which is displacement and thematic mapping as well.
Yeah, after that.
Yep.
So we had 4 sessions on deformation and displacements, and I give this on behalf of 8 chairpersons of these sessions. It is a short summary and some keywords from different presentations and posters. In these sessions, there are various applications presented: landslides, land, coastal subsidence, sinkholes, peatlands, agricultural areas, permafrost, and infrastructure monitoring. Regarding methods, PSI for slowly moving targets, complemented by distributed scatterers, and single pair approaches for faster moving and seasonally decorrelating areas. Also using of artificial reflectors. Some measurement challenges was reported regarding spatiotemporal coherence gaps and the risk of subsampling complex deformation signals. Some improving robustness was reported: integration of physical modeling, combined C and L band observation, complementary INSAR processing strategies, and process-based interpretation of deformation. Some emerging products. It was lots of different efforts from different groups regarding 3D deformation retrieval and growing focus on hazards and risk indicators, such as differential settlement, deformation gradients, angular distortion, population exposures, and different risk and hazards metrics. And efforts towards operational monitoring, advances in large-scale and near real-time processing, sequential analysis, instantaneous state INSAR, together with integration of INSAR with GNSS, ground sensors, physical models, digital twin framework for operational monitoring and early warning applications. These are general keywords from all posters and presentations. In the roundtable discussions, we didn't have specific set questions, but one general set questions regarding 5 different items that what would be the feedback and recommendation. The discussion was, first one was about regarding EGMS. Discussion focused on increasing update frequency, improving product quality in some regions that they have gap or lower quality, enhancing the visibility of validation results, reviewing snow cover masking strategies, and exploring the use of corner reflectors and lots of corner reflectors in different countries for calibration and validation. There was different discussions in the sessions and also in the roundtable regarding quality description of INSAR products, specifically INSAR time series, and something much beyond just error bars, for example, to some universal quality description for phase overlapping, that it is accepted by community and different methodologies. The role of ESA in facilitating and the coordination and supporting R&D activities in this regard was discussed. Regarding geolocation accuracy, the importance of quantifying and documenting geolocation performance across different SAR missions and processing approaches was emphasized with different users in the community. Regarding, is already in this session was discussed about Roselle and Sentinel next generation synergy. This is ongoing discussion about the pros and cons of different modes, convoy modes. It was discussed during the displacement and deformation to have some benefits for different interpretation of applications, deformation, displacement, and long-term star data continuity that the whole community strongly benefit from that, especially in all different disciplines, but specifically in displacement and deformation. Based on all discussions, a couple of general and some of them specific recommendations for ESA. The first one is very obvious, but we want to emphasize on that. Maintain this long-term continuity and accessibility of star data is really, really important for the all different applications. Regarding the Roselle and Sentinel-1 next generation, there was a discussion, but in the end, in this community, we came to recommend it as the convoy configuration as more benefits for the formation and applications. Further support for improving EGMS based on the discussions, and support from ESA for development of a standardized quality descriptors. ESA can support R&D and facilitate community efforts towards common quality standards in this regard. And there was also concerns in these sessions regarding the potential interference of the future, especially geostationary star satellite, C-band star satellite with Sentinel-1. Of course, in the mission design, different phases, these kind of technical issues will be investigated, but the recommendation is very, very early assessment and verification of these interference is very helpful to be done and reported to community. Thank you.
I think we have time for comments or questions, if there are. None. So we have no time, apparently, for comments and questions. So we move on with the next summary, which is for thematic mapping, and the one after will be ice and snow.
So regarding thematic mapping, we have just one slide, just some short summary. We have 10 in total presentations. 5 of them was related to soil moisture retrieval, and the second part was related to tree height. It was also one presentation regarding ocean height estimation from single image phase unwrapping. According to that, our discussions, we can just say one overall recommendation to ESA to prioritize investment in benchmark datasets, validation networks, scalable AI methodologies, multi-frequency SAR exploitation, and future missions concept enabling advanced 3D characterization of vegetation and natural volumes. It was also a lot of discussions about X-band, C-band, and L-band in future systems. So thank you very much.
Thank you, Zibi. Next one is ice and snow, and then we go with current INSA missions.
Okay, well, for ice and snow, we had 2 sessions. In each session, there were 5 presentations, overall 10, and they were actually covering different domains of the cryosphere. Regarding ice sheets, there were 3 presentations, one on showing the monthly and annual Sentinel-1 ice velocity maps and also the discharge from this, from Greenland and Antarctica, and this lasted for the last 11 years, and also the examples for combining L-band and C-band to get these parameters, also in preparation for Roselle. Then we had a presentation showing a long time series of grounding line positions and ice velocity in Antarctica from multi-mission SAR data starting from ERS, including Sentinel-1, of course, but also NISAR.
the first result. And this was primarily focusing on West Antarctica. And then we had a presentation showing the calving font retrieval from Sentinel-1 amplitude images using AI-based methods. Regarding sea ice, there was a very interesting presentation on monitoring and the dynamics of the land-fast ice in the Arctic using Sentinel-1 INSAR data, and in the discussion it came out that it will be also expanded towards Antarctica in the future. For permafrost, we had 3 presentations looking for the ground motion service using Sentinel-1 data for the permafrost regions in Svalbard. We had time series analysis from Sentinel-1 SAR coherence data to look also over permafrost regions in Svalbard, looking for the changes of the coherence depending on the different conditions. And we heard the activities of NASA regarding the validation data collection in the permafrost regions in order to support the NISAR products on permafrost. Regarding snow, there were actually 2 presentations, one on snow height using Tandem X data with a mutual calibration of the DEMs over special regions on glaciers and other regions. And we were looking for PolINSAR and TOMOSAR analysis of airborne FSAR data for the conditions of icy roads in Canada. And there were many more very interesting posters in the poster sessions yesterday. Now we had overall 4 seed questions in order to guide the discussions regarding ice and snow. The first one was dealing with the sensor configuration and acquisition strategies which are preferred to improve the ice sheet products, sea ice products, glaciers, but also snow products. Regarding ice sheet, the recommendation is that we need, in order to proceed with the phase-based approach, which provides higher quality than offset tracking. And for this, we need the crossing orbits, so ascending and descending for Greenland and Antarctica, and also the smaller ice caps in the Arctic and Antarctic region. And this is, of course, also a coordination between Sentinel-1 and ROSEL. Then what should be planned already in advance is a coordinated acquisition strategy of L and C band in order to allow a joint use of these both sensors for monitoring ice sheet-wide parameter retrieval. Regarding the multipolarization data over ice sheets, there are currently only a few data sets available, and more data sets should be acquired to have to allow also polarimetric investigations over ice sheets. And we also discussed the added value of third-party missions as a kind of opportunity to augment the agency program for acquiring data and monitoring the ice parameters. The second question is dedicated to acquisition campaigns, such as the Sentinel-1 repeat acquisition opportunity we had in this spring period, if they are scientifically useful, and if similar campaigns should be repeated and planned for the upcoming missions. And I think Nuno already presented that this is, if there's the opportunity, we will do it. So this is also a recommendation from our group, from the Snow and Ice community, that such opportunities should be taken. And even if it's only a short period, it's very valuable because we can study different processes. Then we asked, is there any need for Calval activities for upcoming SAR missions? For example, ROSEL, Harmony, Sentinel-1, first and next generation. Actually, especially there's a very limited coverage of validation data in polar regions, especially in Antarctica, but also in Greenland. And we think in order to assess the accuracy of these products, activities for Calval should be planned, and in order to support the retrieval of the parameters from the various sensors. Something is also important, that these parameters or validation data should be made available to the community publicable. Now, we also addressed the analysis-ready SAR INSAR datasets for the snow and ice monitoring if there is any need of the products, if already some people are using them, which ARD products are most needed, geocoded INSAR, for example, or which timestamps are needed, and other products. And actually, we found out that most of the participants did not request ARD products or did not look into detail for that. Most of those were really dealing with SLC data. And there was only a very limited experience for this. What could be quite interesting was mentioned is that co-registered repeat pass SLC data based on the one single primary master and or an alternative strategy could be used. Further experience but is needed for ARD data in the community in order to assess this question. And I think that was it.
Thank you, Thomas. Next one is, yes, INSAR current missions, and after that, earthquakes and tectonics.
I think that this session was from Muriel and Marco, which are not there, so I'm taking it on their behalf.
So yeah, it was current INSAR mission. So I'm sorry, I'm going to read now. So 5 presentations, mainly covering L-band missions, 3 presentations on NISAR, one from URSS on Pulsar 2 and Pulsar 3, and a very nice one on Chinese SAR missions, so mini missions, Lutan, Gaofen, Tianyi, Lutan 4. So NISAR is working nominally and is delivering unprecedented L-band time series with a suite of innovative products. So GSLCs, but much more than GSLCs. Pulsar offers opportunity for cross-mode and cross-sensor INSAR. China has a fleet of non-free multi-frequency SAR suitable for a range of INSAR applications. So recommendations that was placed during this session. So more S-band data from NISAR mission, and also something which was getting a lot of traction, which is the establishment of support side in or outside China in order to be able to access this fantastic Chinese data. So seed questions. What are the community expectation challenges, and when start working with L-band NISAR time series? Similarly to what Thomas was presenting, are the GSLC, which is a kind of ARD, the future of SAR products, what is needed to improve them and to make them robust? So it's kind of a similar problematic there. Do we understand the corrections needed at L-band versus C-band and to generate accurate INSAR results? And what are the opportunities for combining L-band, S-band, and what I've seen with previous sessions, also S-band time series? It's not working anymore. Well, and that's it. So, thank you very much.
Thank you, Nuno. So next one is then earthquakes and tectonics, followed by biomass.
Okay, thank you. So there are a bunch of us presenting on quite a large number of session chairs here. So we had 15 talks. I think Johnny counted more than 120 people in the room. So we also had a very lively poster session. I think in general, the presentation showed the kind of maturity of INSAR as a tool for earthquakes and tectonics, covered applications that range from really small earthquakes, often induced by human activity, human exploitation of the subsurface like mining, through to the earthquake cycle for large damaging events, and large regional tectonic strain fields were shown for very, very large regions, and there were technical advances such as the extended burst overlap interferometry. I think it's clear from the general way the community is going that measuring and modeling time-dependent behavior is becoming increasingly important. So we thought normally ESA get a lot of recommendations, and there will be some of those, so don't worry. But we thought we'd make some recommendations for us as a community as well. So I think we should self-organize to identify any gaps in coverage from Sentinel-1 and make consolidated recommendations to ESA. I think these are more useful than individual groups saying we're missing a track here or we're missing somewhere else. We also, I guess this links into Ramon's point about kind of INSAR trust, etc. But given the number of regional velocity and strain field products now available, an inter-comparison activity should take place, and that should really focus on understanding uncertainties and the impacts of different approaches. We should continue to exploit this 30-plus year extensive archive of ESSR data, which is an incredible resource for tectonics. Then there's some for ESA as well. So where possible, improve coverage for Sentinel-1 in priority areas identified by the community. So in some cases, that might be adding the second viewing geometry or increasing to 6-day coverage. We recognize that there are constraints on that. And so actually using the community priorities and then working out what's possible in a dialogue is really the recommendation there. So we had a discussion about this extended burst overlap interferometry, and this is probably an impossible request at this stage, but consider modifying the SLC focusing during the upcoming reprocessing effort to extend the burst coverage. It's obviously particularly useful for obtaining north-south motions from burst overlap interferometry, but it does also extend the width of the SLCs, so there's more data. This is useful for tectonics, but also for things like land subsidence, volcanoes, and a large number of applications, I think, would find this useful. It may be that could be done in certain regions, and obviously, as a minimum, I think, providing the tools and supporting the tools that are going to be kind of open source to make that possible. Related to that, ensuring that future missions are configured to have sensitivity to north-south motion or azimuth motion strictly is important as well, and that seems to be technically feasible. So I guess we disagree with some of the comments earlier. So the community could see some advantages of the convoy mode, and we had a discussion about that, but having shorter revisit times for event response is a strong priority for this community. And we did wonder whether it's really a binary choice between convoy mode and equally spaced. So I think I fully endorse Ramon's suggestion for a study to just investigate the pros and cons of different options. But you could imagine, for example, having one of the Sentinel-1 Next Generation and Roselle's flying together, and the other two spaced at +4 days and +8 days, for example, or we've heard of +1 day recommendation. So there's a number of options there, and I think it'd be good to explore all of those and try and weigh up what the different communities want. Sorry, there's more. I think ESA does a great job at preserving and archiving the legacy data. Just want to make sure that includes the raw data and SLC data. Legacy mission data should be made as easy to obtain access and use as Sentinel-1 data. This is probably too late, but there's a number of people have mentioned that there's ERS data. Some of that, the raw data, has been discarded because of missing lines. And we just wanted to make the point that it can still be useful even despite the missing lines. But I think in many cases, it's probably too late for that. We can go into more examples if you like, but there's very specific examples where people have gone back to old earthquakes to reprocess them, and the data aren't there in the archive. Luckily, we can normally find it somewhere amongst the community, but there are data that have gone from the archive. So the small orbital tube is important, as we've had for most of the Sentinel-1 mission. There was a request about improving download speeds, perhaps also making the data available in smaller packages, and for example, VV only or burst ID based downloads. Sorry, there's more. So process and make Sentinel-1 extended wide swath SLC data. I think that was mentioned earlier on as well. I think particularly in the northern latitudes, places like Iceland, where there's a lot of this data, could be really useful. Okay, then we had a few about the meeting in general. Firstly, this is a great meeting, so I wanted to thank ESA, Marcus, and the local organising team for that. It's been a really, really successful. Please continue. I think the tectonics community really values it. Every 3 years seems to be about right. I think we had a recommendation to ensure the programme is confirmed a little bit earlier, so maybe just advance the timeline a little bit, which will help some of our international speakers and presenters to obtain visas in time. We had a few cancellations in our session. And continue the work that ESA is doing to improve diversity. So I speak here as an ageing white man, but yes, try and improve the diversity of session chairs. I think there's probably time for the next generation of session chairs as well as the next generation of satellites. Okay, on that note, I will leave the stage, never to be heard of again. Thank you.
Very good. Thank you very much, Tim. I think that now we move to the biomass, right? So who is there from? I think it's okay.
I'll actually start with, I heard it twice, just on a comment for Hydroterra Plus, to reassure the displacement community, there is no impact to Sentinel-1 next generation. It's going to be launched in 2036. If it's accepted, we will make this clear, so it's the opposite the problem. So the impact to Hydroterra Plus, but we will make this clear, so we took the point. Now, on biomass, this was yesterday. We had 10 talks. This was the first Fringe after the launch, so there were general presentation alongside more detailed presentations. A few highlights. For the first time in ESA history, insert-derived products are generated with a processor internal to the mission. This includes ionospheric correction, multi-layer, systematic estimation of terrain phase, and the delivery of phase-calibrated data stacks, level 1C. And a highlight, this is actually common to explorers. I think a cool thing of Earth Explorer is really when you unlock new science, right? Or you make new discovery. And something that that scientists discovers is that over Amazonia, they found out complex phenomena, and this was related to changing weather conditions. So whereas this complicates the primary objective of the mission, so the forest retrieval, structure retrieval, it points out new and unexplored possibility to characterize hydrological phenomena in tropical forests. So a few other highlights on the processing methods. So they have been considered to remove terrain or volume scattering with potential beneficial effects for forestry and characterization of the terrain below. And we also had a couple of talks showing and confirming the biomass potential in mapping terrain topography below the vegetation. Tomography is obviously part of the mission, so they have shown how tomographic data has been successfully produced by the internal processor as well as by independent research groups. Couple of secondary, let's say, objectives. One on ice velocity. So biomass has been shown capable of mapping ice velocity in Antarctica with ascending-descending data stacks. And this was promising despite the ionosphere. And it's shown also complementarity with Sentinel-1 products. So, and we were discussing also about synergy on that for the future. Not only velocity, but also mapping grounding lines and subglacial hydrological dynamics. And another science area was on geological remote sensing. So there was a talk showing a clear potential in mapping geological features. This was over an area in the Sahara Desert. It's clear, so when you see this image, it's actually really cool to see the connection with subsurface geology and a quantitative mapping of geometry by the topography. I think something that is also interesting is that is the penetration of the signal into sand. So this has been shown to detect structure down to 10 meters below the surface. We also had a roundtable, an open discussion, so with few seed questions. So the first one was on processing. Biomass implements a sophisticated insert processor to produce data coherence and phase-calibrated data. This brings improvements in many cases, but of course it's not perfect and needs development. We asked about feelings. Generally speaking, the audience was happy about that, so level 1C products are well accepted. There was one remark on investigating the consistencies across stacks, calibrated stacks, in order to strengthen trust in this type of product. Just the note was that INSAR expert can always access level 1A data for which this correction has not been applied. So this can be done also not with the nominal processor. There was also a lively discussion about the option to deliver geocoded SLC. So we had also Marco Lavalle from the NISAR team in the table. So there was like a nice discussion about that. So the general agreement was that GSLCs are useful. So this is no doubt, but also radar geometry data. So this is quite a democratic statement. And finally, open science is confirmed important, generally, but of course in biomass as well. And the last slide with two more questions. So synergy with NISAR, how to implement them. Here, the understanding of the processing chain is key, so to get a proper comparison of biomass and NISAR, and the community welcomes detailed data notation to get this integration done properly. And both missions will benefit from common and well-documented geophysical Calval sites. And the final question was like more general, so around like what I mentioned before, what is new, which exciting new application we can open with biomass. Biodiversity was mentioned, so obviously passing through forest structure can enable this. Water-related phenomena, so this is something that has been presented also. So for example, flooding, soil moisture under the vegetation, water accumulation. Geological remote sensing, so subsurface geological structure, and why not archaeology. And mapping a ionosphere in 4D. So this is also today I heard a few times like that a ionosphere is like like the bad thing that we need to correct for. But actually, the mapping of it can be unlocked with biomass. And I mentioned on Tuesday about a workshop where ESA is trying to link the, let's say, atmospheric community, mainly coming from swarm, and the star community, mainly coming from this the INSAR, mainly yourself. I mentioned the wrong date. I said the 15th of October. This is actually the Nightlight workshop. That is the week before. The right date is the 20th of October. So the 20th and the 22nd of October, we will have a 4D ionosphere workshop where I invite you to attend. We really try here to link the communities so that we have we do studies together and we start to talk to each other. Okay, this is it. Thank you.
Thank you. Then we move to bistatic/harmony, and after that is the last one, landslides.
All right, we were just this morning, so we haven't had a lot of time to prepare, so this is going to be very short. Also, Paco's disappeared already. So this is our one-page summary. So we had a very short session. The presentations covered the scientific applications of Harmony, trying to map the objectives to the product tree, the acquisition masks, and also the technical developments in terms of the processing algorithms for squint geometry, penetration-dependent elevation bias, and phase synchronization approaches. So the main conclusions and recommendations. We had a seed question asking about whether the community were interested in a reference DEM that was global in scope. The answer is yes. We kind of thought it would be, but we have extremely enthusiastic support for doing this during each of the XTI phases, the cross-track interferometry phases, because we spent quite a while discussing all the possible uses that could be made of this, but there's a huge community support for this. One of the seed questions was whether there are additional science questions that require multi-static missions. We came up with two. One is landslides. So the frequency volume distribution of landslides is very poorly known, and it's an important parameter for understanding landslides and also understanding hazards. So there is a recommendation to think about expanding the Harmony mask for topographic change to include some high priority landslide regions. We did note that actually in the three-dimensional velocities for landslides are probably already going to be covered because the tectonic strain mask is already operating at three-dimensional velocities. And then forestry, this is really not my field, I'm not going to say more about this, but there are lots of forestry applications for multi-static missions. Harmony may help with some of these, but L-band in particular, multi-static L-band missions in particular. And our final recommendation, all SAR missions should have companions or co-flyers. And multi-static polarimetry could also be interesting, but it needs quite a lot more exploration. That's it. Thank you.
Thank you. And now we have the last one, that is landslides.
Thank you very much. Yes, we were also last thing this morning, so excuse us if we've made any mistakes trying to hurriedly transcribe all the comments in the coffee break. So we were quite a short session. We had 4 excellent presentations, but also I think it's worth mentioning quite a lot of really good posters. Hopefully you all managed to catch those in the poster session yesterday. And then in the session themes, we had a broader kind of use of INSAR and SAR for landslide hazards, not just monitoring deformation, but linking in surface motion, triggering conditions, terrain contexts. And I think it was really important to note that the landslide interpretation needs that context, so things like the rainfall history, the soil moisture. Different SAR products are revealing different parts of the problem, so different bands, time series wrapped into ferrograms get used as well as, say, the more sort of the longer time series products. And then factors like coherence, reliability layers, and the interpretation is becoming more robust. These applications aren't just experimental, but there are a lot of operational systems using this data and these techniques. So we had a couple of seed questions based on the things that we'd heard discussed previously and some of the open questions that ESA had proposed earlier in the sessions. So just trying to go through the summaries of those. One of the biggest limitations of the landslide studies that we felt was 3D components. So there are things which are going to help us, things like Harmony, but we need to also look at the long-term operational availability of those, and also things like access to third-party novel missions to try and make sure that we've got the longer time series of those available, as well as just snapshots, short snapshots in time. And again, higher resolution is always requested, and I know ESA are limited in what they can do, but also, again, maybe looking at access to third-party missions for those. We had a discussion on soil moisture, which I know came up before, and I think we would echo the requests for maybe more work on validation and open validation data sets with in situ data that we can then use to develop some of these algorithms and capabilities. The analysis-ready data sets, again, open up access to some of these things for a wider range of users, which is great. But I think we would echo the comments from the other sessions about making sure that there is always access to the earlier stages of those data sets, because as soon as you start changing the data to make them analysis ready, you're ruling out other information. You're stopping people doing some of the earlier upstream science that might be useful. One thing that perhaps didn't come up across Fringe as much as it had done is something I think ESA is now consistently getting right, and we probably don't say that enough, is making sure that we have those long, consistent, interoperable time series that we can rely on over time for operational products. And I think there's now a really good history of that. There was a concern, I think someone's already mentioned, with the reprocessing campaign, that can we please make sure that we have access to the older data until we're able to start using the new data, and things about re-downloads and so on. And then one other recommendation was, somebody raised the point that there is a high-resolution DEM available across the whole of Europe, but that's very restricted access, and within the landslides community, there is a need for high-resolution topography. So are there data sets where the access could be expanded? Are there opportunities for acquiring new data sets? I think that was us.
Thank you, Rachel. So that was the last of the summaries. So now it's time for me to say a couple of closing remarks.
I have to say that, as many people have told me, this has been a really nice Fringe, and I've been involved with the organization for 10 times, and I have never seen the community this excited. I mean, we have new satellites and new types of data, so it's been a super nice one. And things have been running smoothly, and just by numbers, I mean, we are largest ever, more than 500 people, 48 countries. And yeah, there's, you were in the workshop, I just picked up some high-level thematic highlights. Sentinel-1, biomass, NISAR, Chinese missions even. This shows again the people who attended. Yeah, I mean, this was a really nice one, and this doesn't happen alone, so I had to thank many people to make this possible. So just to start with all the teams involved with the organizations, we have the Serco team, so there is Magdalena, Ulla, Melissa, and thanks for the Snap presentation booth. And then there's the... Actually, I should pick up Ulla and Magda first from... is Magda here? I mean, you should stand up and get a standing ovation, because it's Ulla and Magda who made it work. So as they were joking to me, so Magda was the brains and Ulla was the muscle. So this one went really nicely. Then I have to thank the Olli team for the logistics and many things that were happening in the background. Matteo, Francesca, Riccardo, Margherita, and Lorenzo. Then I have to thank JGB Productions for these fantastic screens that really were the highlight of the workshop, quite literally. So this is how interferogram should be viewed in perpetuity, I think. Yes, I have to thank the EOGB team, the graphics bureau in Esrin for the graphics. Magda has been mentioned. Then super thanks to Professor Zibi, the local organizer. You should also stand up and... Things were really running smoothly here on site, and this venue is superb, so this was really nice. Then also big thanks for the scientific committee and the chairpersons for their contributions on vetting the abstracts and setting the program up. So I think that's about it. So we are looking forward to the next Fringe. So we have some time. So if somebody wants to make any proposals or recommendations for next Fringe, now would be still the time. So anyone? In person, I've had several quite nice remarks, but if there is nothing, then I think that we can close here. Thank you, and see you latest in 3 years in an undisclosed location. Thank you.